The universe is a place of endless mysteries, where the laws of physics bend and twist in ways that defy explanation. Picture this: somewhere in the vast expanse of space, there's a star that's over 2 million degrees hotter than the surface of our sun, yet no one can figure out why. Or consider the eerie, repeating radio signals from deep space that pulse with such precision, they almost seem artificial. These aren't plot twists from a sci-fi novel. They're real, baffling phenomena that scientists are still scrambling to understand. And today, we're diving into 50 of the strangest, most mind-bending cosmic enigmas ever recorded, events so bizarre, they'll make you question everything you thought you knew about the cosmos. What if I told you that somewhere out there, an entire galaxy is missing its dark matter, the invisible glue that holds the universe together? Or that black holes, those cosmic vacuum cleaners, might actually be leaking information they were supposed to swallow forever? These aren't just curiosities, they're clues that the universe is far weirder, far more unpredictable than we ever imagined. From stars that vanish without a trace to galaxies that spin backward against the laws of physics, each of these phenomena challenges our understanding of reality itself. And the deeper we look, the clearer it becomes. Space isn't just empty darkness. It's a stage for the most extraordinary, inexplicable performances in existence. So why does any of this matter? Because every strange flicker, every cosmic anomaly, is a piece of a puzzle we're only beginning to assemble. These aren't just distant oddities, they're windows into the fundamental nature of reality, hints that the universe still has secrets it's not ready to reveal. Whether it's a planet that shouldn't exist or a signal that repeats like clockwork from the void, each one invites us to ask, what else is out there? What don't we know? That's the journey we're embarking on today, a voyage through the most bewildering, awe-inspiring moments in the history of the cosmos. Ready to have your mind stretched? Let's begin. Even the biggest cosmic event of all, the Big Bang, is full of holes that leave scientists scratching their heads. Take the simplest question: why does anything exist at all? According to physics, matter and antimatter should have cancelled each other out in a burst of energy, leaving behind nothing but empty space. And yet, here we are. So where did all that extra matter come from? Some think tiny asymmetries in the early universe tipped the scales, while others suggest undiscovered particles might be the missing piece. Then there's dark matter, invisible, untouchable, yet making up over a quarter of the cosmos. We can see its gravitational pull shaping galaxies, but after decades of searching, we still don't know what it actually is. And if that weren't strange enough, the universe isn't just expanding, it's speeding up, as if some unseen force is pushing it apart. Scientists call it dark energy, but that's just a name for something we can't explain. Some theories point to quantum fluctuations, tiny bursts of energy flickering in and out of existence, while others suggest gravity itself might behave differently on cosmic scales. The Big Bang didn't just create the universe, it left behind a trail of riddles we're still trying to solve. Right in our cosmic backyard, something massive is pulling us, and everything around us toward it at over 1 million miles per hour. Astronomers call it the Great Attractor, a gravitational behemoth lurking in the Centaurus supercluster. But here's what's really strange: we can't see it. This thing has the mass of tens of thousands of Milky Ways, yet it hides behind what scientists call the zone of avoidance, a thick curtain of stars, gas, and dust along the plane of our own galaxy that blocks our view. It's like trying to spot a lighthouse through a thunderstorm. What makes this even weirder is how it defies expectations. Normally, massive objects like galaxy clusters reveal themselves through visible light or X-rays, but the Great Attractor barely registers. Some researchers think it might be a supercluster we don't fully understand, while others speculate it could be something even larger, a previously unknown structure weaving galaxies together like cosmic puppet strings. And it's not just pulling us. Entire galaxies, some hundreds of millions of light years away, are caught in its tug of war. The real mystery: we might be missing half the story. The zone of avoidance obscures nearly 20% of the sky, creating a blind spot in our cosmic map. Infrared telescopes and radio waves have peeled back some layers, revealing hints of hidden galaxies, but the heart of the Great Attractor remains elusive. Could there be something even bigger behind it? One theory suggests it's just the tip of the iceberg, that a colossal structure called the Shapley supercluster farther beyond might be the true mastermind. Until we find a way to peer through the cosmic fog, this gravitational enigma will keep dragging us toward the unknown. Think about holding a flashlight in a pitch-black room. What you see is just a sliver of what's actually there. That's exactly how it is with our universe. Everything we can observe, stars, galaxies, planets, makes up less than 5% of the cosmos. The rest, a pair of invisible, enigmatic forces called dark matter and dark energy, quietly pulling and pushing the universe in ways we're only beginning to grasp. Dark matter first revealed itself not by what we could see, but by what we couldn't. Back in the 1930s, astronomer Fritz Zwicky noticed something bizarre about the Coma Cluster, a group of galaxies over 300 million light-years away. Even though the visible mass of those galaxies couldn't account for it, they were moving so fast they should have flown apart. Something unseen was holding them together. Decades later, Vera Rubin found the same anomaly in spinning galaxies, where stars on the outer edges whirled just as fast as those near the center, defying gravity's rules unless some invisible mass was anchoring them. That's the essence of dark matter. It doesn't emit, absorb, or reflect light, yet its gravitational grip shapes the very structure of the cosmos, weaving galaxies into vast, intricate webs. But if dark matter is the universe's hidden scaffold, dark energy is its mysterious engine. In the late 90s, two teams of astronomers studying distant supernova made a shocking discovery. Instead of slowing down, the expansion of the universe was speeding up. It was like tossing a ball in the air only to watch it shoot faster into the sky. Whatever's causing this, dubbed dark energy, isn't just invisible. It behaves like an anti-gravity force stretching space itself. Some theories suggest it's a property of empty space, a cosmic repulsion embedded in the fabric of reality. Others speculate it could be an entirely new form of energy, one that grows stronger as the universe expands. The wildest part: these two forces aren't just lurking in some distant corner of space, they're everywhere. Dark matter's pull guides the paths of stars in our own Milky Way, while dark energy's push dictates the universe's ultimate fate, possibly leading to a distant future where galaxies are ripped apart in a big rip. Yet despite decades of hunting, we still don't know what they truly are. Particle colliders search for hypothetical dark matter particles, while space telescopes map dark energy's fingerprints, but the answers remain frustratingly out of reach. So why does this matter? Because dark matter and dark energy aren't just cosmic footnotes, they're proof that the universe is far stranger than our best theories predict. They remind us that what we see is just the tip of the iceberg, and somewhere in that vast, invisible 95%, the universe's greatest secrets are still waiting to be uncovered. Imagine a universe so vast that there are more stars in the observable cosmos than grains of sand on every beach on Earth. With numbers like that, the odds of other intelligent civilizations out there seem almost certain. And yet silence, no signals, no visits, no trace. This glaring contradiction is the Fermi Paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" If life is so likely, why does the universe feel so empty? One unsettling answer is the Great Filter, a hypothetical barrier that prevents life from advancing beyond a certain point. Think of it like a cosmic obstacle course where most civilizations fail, whether it's self-destruction through war or climate collapse, or some universal trap we haven't encountered yet. The frightening possibility: we might not have passed the filter, If most life gets wiped out before reaching interstellar communication, that could explain the eerie quiet. Or worse, what if the filter lies ahead of us, lurking in our future? Then there's the zoo hypothesis, which suggests that advanced civilizations might already know we're here but choose not to interfere, treating Earth like a protected wildlife reserve. It's a comforting thought until you consider how humans treat animals in zoos. Would we really want to be someone else's experiment? Other theories are even wilder. Maybe aliens operate on timescales too slow for us to perceive, or they've transcended physical form entirely, existing as digital consciousness in some galactic cloud. The paradox forces us to confront uncomfortable truths. Either we're catastrophically alone, or the universe is teeming with life that's deliberately hiding. Both possibilities are equally unnerving. Every silent radio telescope, every empty patch of space, whispers the same question. Are we missing something fundamental about life itself, or is the universe playing a game we don't yet understand the rules to? One of the most fleeting yet explosive mysteries in the cosmos lasts just a fraction of a second. Fast radio bursts, or FRB. These incredibly bright blasts of radio waves pack more energy than our sun emits in 80 years, yet vanish almost as quickly as they appear. The first one was discovered by accident in 2007, buried in old telescope data, and since then we've detected hundreds more streaking across the universe. What makes them even stranger is their unpredictability. Most FRBs fire once and never repeat, cosmic one-hit wonders that leave astronomers scrambling to pinpoint their origins. But a handful defy expectations, sending out repeated signals like clockwork. Take FRB 1211, for instance, which pulses every 157 days like a celestial metronome. Then there's FRB 1809, repeating so frequently that scientists could finally trace it back to a tiny, turbulent galaxy 3 billion light-years away. So what's causing these bursts? One leading suspect is magnetars, neutron stars with magnetic fields so powerful they could strip the information from a credit card halfway across the Milky Way. Picture a magnetar's crust cracking under immense strain, releasing a shockwave of energy that ripples through space as an FRB. But not all FRBs fit this explanation. Some repeat with patterns too regular, others erupt from regions with no magnetars in sight. That's led to wilder theories like colliding black holes or even, yes, alien megastructures. The idea is controversial, but when nature doesn't offer easy answers, even fringe possibilities get a second look. The real puzzle is why some repeat while others don't. Are they different phenomena altogether, or just different stages of the same cataclysmic process? Some scientists think non-repeaters might be the final, self-destructive outbursts of dying objects, while repeaters could be younger, more stable systems. Others suggest it's all about perspective. What looks like a one-off burst from Earth might actually be a repeater whose signals are too faint or misaligned for us to catch again. Every new FRB discovery peels back another layer of the mystery. Telescopes like CHIME in Canada are now scanning the skies around the clock, turning up dozens of bursts a month. With each detection, we get closer to understanding what's sending these cryptic messages across the cosmos. Are they the screams of dying stars, the tremors of unseen physics, or something even more extraordinary? For now, fast radio bursts remain one of space's most tantalizing enigmas, brief, brilliant, and brimming with questions we're only beginning to ask. On a quiet August night in 1977, a radio telescope in Ohio picked up something extraordinary. A signal so powerful and unusual that astronomer Jerry Rabel circled it on the printout and scribbled, "Wow." Next to it in red ink, that 72-second burst of radio waves coming from the direction of the constellation Sagittarius remains one of the most tantalizing mysteries in the search for extraterrestrial intelligence. What made it special wasn't just its strength, 30 times louder than the cosmic background noise, but its frequency. It hit exactly 1,420 MHz, a silent channel where natural cosmic phenomena rarely emit, and one that hydrogen, the most common element in the universe, just happens to absorb and emit. A frequency, in other words, that aliens might logically choose to shout into the void. For decades, scientists have tried to explain it away. Could it have been a passing satellite? Unlikely, no known human-made object matched its profile. A reflection of earthly radio noise bouncing off space debris. The signal's narrow frequency range and clean shape don't fit that messy scenario. Some suggested a comet, but the two candidates near the signal's origin point weren't even discovered until years later, and comets don't emit strong radio waves at that frequency anyway. The most plausible natural explanation, a freak astrophysical event like a star's plasma eruption, doesn't quite line up either, since the signal never repeated despite over 50 follow-up attempts. That's the heart of the mystery. The wow signal wasn't just loud, it was fleeting, like a cosmic scream that cuts off mid-breath. If it was an alien broadcast, why only 72 seconds? Was it a targeted beacon sweeping past Earth, a malfunctioning transmitter, or more chillingly, a message we weren't meant to hear long enough to decode? The signal's intensity suggests it came from something within our galaxy, perhaps even as close as a nearby star system. Yet without repetition, it's impossible to confirm. The irony, the same telescope that caught the signal was part of SETI's early efforts to scan the skies systematically, proof that even when we're listening, the universe might send us a puzzle with no answer key. Today, improved telescopes and machine learning scour the skies for similar anomalies, but the wow signal stands alone, a blip that refuses to be forgotten, a whisper from the cosmos that still dares us to wonder. In the constellation Cygnus, there's a star that behaves like nothing else we've ever seen, KC 8462852, better known as Tabby's star. Named after astronomer Tabby Boyajian, who first documented its bizarre light patterns, this star doesn't flicker or pulse like ordinary variable stars. Instead, it dims erratically, sometimes dropping in brightness by up to 22% for days or even weeks at a time, as if something colossal is passing in front of it. And when scientists checked the data, they found these weren't smooth, predictable dips. They were jagged, asymmetrical, and utterly chaotic. The mystery deepened when astronomers dug into old photographic plates and discovered something even stranger. Over the past century, Tabby's star appears to have faded by a staggering 14%. Stars this age simply don't do that, not without a catastrophic explanation. So what's blocking its light? One early, provocative theory suggested an alien megastructure like a Dyson swarm, a hypothetical array of energy-collecting satellites built by an advanced civilization. The idea wasn't entirely far-fetched. The star's light patterns didn't match any known natural phenomenon. But while it captured imaginations, scientists quickly turned to more plausible, if still puzzling, explanations. Dust seems the most likely culprit, not ordinary dust, but vast, uneven clouds of it, possibly from cometary fragments or the aftermath of a planetary collision. Infrared observations show excess heat around the star, consistent with dust absorbing and re-radiating light. Yet even this theory has holes. Dust should scatter certain wavelengths of light in predictable ways, and Tabby's star's dimming doesn't always follow those rules. Some researchers propose a rogue planet with trailing debris, or even a distorted star spot, a magnetic blemish on the star's surface, though none fully account for the extreme aperiodic dimming. The most compelling natural explanation, a family of giant exocomets, some as large as planets, breaking apart in chaotic orbits around the star. As they disintegrate, they could cast irregular shadows across its face, creating the observed dips. But even this leaves questions. Why so many comets, and why haven't we seen similar patterns around other stars? Tabby's star remains an outlier, a cosmic oddball that refuses to fit neatly into any box. What makes this star so fascinating isn't just the mystery, it's what it reveals about how we explore the unknown. When nature throws us a curveball, our first instinct is to reach for the extraordinary, like aliens. But more often, the truth is something we just haven't seen before. Tabby's star reminds us that the universe is full of surprises, and sometimes the most profound discoveries begin with a single, inexplicable flicker in the data. Black holes aren't just cosmic vacuum cleaners, they're also universe-sized shredders, tearing apart everything that falls in and seemingly erasing it from existence. Or at least that's what physicists thought for decades. But here's the problem: quantum mechanics, the rulebook for how particles behave, says information can never truly be destroyed. It might get scrambled or hidden, but it can't vanish without a trace. So when a black hole swallows a star, what happens to all that information? This contradiction is the black hole information paradox, and it's one of the most heated debates in modern physics. The trouble started with Stephen Hawking's groundbreaking work in the 1970s. He realized black holes aren't completely black, they slowly leak energy, now called Hawking radiation. Over unimaginable eons, this radiation causes black holes to evaporate entirely. But here's the catch: Hawking radiation appears totally random, carrying no trace of what fell into the black hole. If the hole vanishes, all the information about the particles it consumed would vanish too, violating quantum mechanics' core principle. It's like burning a library and claiming the smoke somehow contains every word from every book, except the smoke is featureless, identical no matter what you burn. Some physicists argue the information isn't lost, it's just trapped inside the black hole's remnant, encoded in ways we don't yet understand. Others propose wilder solutions, like the idea that black holes don't actually destroy information but spit it back out through quantum entanglement, a phenomenon Einstein famously called spooky action at a distance. Imagine two particles linked across space change one, and the other instantly reacts. Some theories suggest Hawking radiation pairs could be entangled with particles inside the black hole, preserving information in a cosmic game of telephone. Then there's the holographic principle, which suggests all the information swallowed by a black hole isn't lost but smeared across its event horizon like a hologram. Think of it like encoding a three-dimensional movie on a two-dimensional DVD. The data's still there, just rewritten in a form we can't yet decode. String theorists take this further, proposing that black holes might be tangled knots of vibrating strings with information stored in their complex vibrations. But the most mind-bending possibility, that the paradox reveals a flaw in our understanding of space-time itself. If space is fundamentally pixelated, built from tiny, indivisible units, then black holes might be forcing us to rewrite physics at the most basic level. Until we crack this puzzle, black holes will remain cosmic enigmas, not just crushing matter, but crushing our assumptions about how the universe works. The cosmic microwave background, the faint glow left over from the Big Bang, should be the ultimate cosmic Rorschach test, a random splatter of hot and cold spots revealing no particular direction or pattern. That's what the cosmological principle, a cornerstone of modern astronomy, insists. On large scales, the universe must look the same in all directions, with no special place or orientation. But in 2005, when scientists mapped this ancient light with unprecedented precision, they found something that sent chills down the spines of cosmologists, a bizarre, spine-like alignment of hot and cold spots stretching across the sky like a cosmic fingerprint. They called it the axis of evil, partly as a joke about its unnerving implications, but the name stuck because the discovery threatened to upend one of astronomy's most sacred assumptions. At first, researchers dismissed it as a fluke, an artifact of instrument noise or statistical chance. But with each new generation of satellites, from WMAP to Planck, the alignment persisted. The odds of it being random, less than 1 in 1,000. The axis isn't just a quirky pattern, it points almost directly at the plane of our solar system, as if the universe itself is whispering that we're somehow special. That's heresy in cosmology, where the bedrock idea is that Earth holds no privileged position. If the axis is real, it could mean our local neighborhood is imprinted on the fabric of the cosmos, or worse, that the cosmological principle is fundamentally wrong. Some theorists scramble for less earth-shattering explanations. Maybe our galaxy's dust distorts the CMB in ways we haven't fully accounted for, or perhaps the solar system's motion creates an illusion of alignment. Others propose wilder fixes like pre-Big Bang physics leaving echoes in space-time, or even a universe that's lopsided on scales larger than we can observe. Then there's the multiverse angle. If our universe is one bubble among infinite others, its collisions with neighboring bubbles might have left scars visible in the CMB. The most unsettling possibility, that the axis hints at a universe with a built-in direction, a cosmic north that defies our expectations of uniformity. For now, the debate rages on, with some calling it the most underrated mystery in cosmology, while others insist it's just a date, a glitch waiting to be resolved. But the axis of evil lingers, a silent challenge to our most cherished assumptions, proof that even the oldest light in the universe still has secrets to spill. If you took a spaceship into the depths of the constellation Boötes, you'd find yourself in one of the eeriest places in the cosmos, a yawning chasm of nothingness so vast it defies logic. The Boötes void spans an astonishing 330 million light-years, a region where galaxies should be packed shoulder to shoulder like a crowded city. Instead, it's more like a ghost town with only a handful of galaxies scattered across a space that could comfortably hold thousands. This cosmic desert isn't just empty, it's unnaturally empty, as if someone carved a hole straight through the universe. So how does a void this colossal even form? One leading theory points to the fingerprints of the early universe. In the chaotic aftermath of the Big Bang, quantum fluctuations created slight density differences, some regions slightly denser, others slightly emptier. Over billions of years, gravity amplified these differences, pulling matter into the denser areas and leaving behind vast, barren bubbles. But the Boötes void pushes this idea to its limits. It's too big, too empty, challenging our models of cosmic evolution. Some scientists speculate it might be the result of multiple smaller voids merging, like soap bubbles combining into one giant cavity. Others wonder if an unknown force, something beyond dark energy, might have accelerated matter away from this region, leaving behind a vacuum. Then there's the eerie possibility that the void isn't empty at all. What if it's filled with invisible dark matter, or even stranger, a new form of exotic matter that neither emits nor absorbs light? Telescopes can't see it, but its gravitational influence could explain why so few galaxies have formed there. And if that weren't unsettling enough, some cosmologists have floated the idea that the Boötes void might be evidence of a collision with another universe, a bruise left by a parallel cosmos brushing against our own in the multiverse. But the real mystery isn't just why the Boötes void exists, it's what its existence means. Voids like this aren't just cosmic oddities, they're backstage passes to the universe's structure. The way galaxies avoid certain regions reveals hidden rules about how gravity and dark energy sculpt the cosmos. The Boötes void, in all its emptiness, forces us to ask, is this just an extreme outlier, or a sign that our understanding of the universe's skeleton is missing something fundamental? The most humbling thought, we might be staring into the void all wrong. Our telescopes scan for galaxies, but what if the void is hiding something else entirely? Dim, failed galaxies shrouded in dust, or rogue black holes drifting unseen. Until we peer deeper, the Boötes void will remain a cosmic paradox, a blank space on the map that's anything but simple. When NASA Pioneer 10 and 11 spacecraft ventured beyond the edges of our solar system, they carried with them humanity's first physical messages to the stars, gold plaques etched with greetings and maps. But as these intrepid probes drifted farther into the void, something unexpected happened. They began slowing down ever so slightly, as if an invisible hand were tugging them backward. This tiny but persistent deceleration became known as the Pioneer Anomaly, a gravitational puzzle that left scientists scratching their heads for decades. At first glance, the numbers seemed insignificant, a slowdown equivalent to just 1/10 billionth of Earth's gravity. But in the precise world of orbital mechanics, where even minute forces can cascade into massive deviations over time, this anomaly was anything but trivial. By the time Pioneer 10 reached the distance of Pluto, the discrepancy had grown to hundreds of thousands of miles off its predicted trajectory. Was it a flaw in our understanding of gravity? A sign of unseen matter lurking in the outer solar system? Or something even stranger? The most tantalizing early theory pointed toward new physics. Some speculated that the anomaly might be evidence of modified gravity, a tweak to Einstein's general relativity that could explain dark matter's effects without invoking invisible particles. Others wondered if it hinted at higher dimensions where gravity leaks away from our observable universe. But as often happens in science, the truth turned out to be both simpler and more humbling. Years of painstaking data analysis revealed that the culprit wasn't cosmic mystery but plain old heat. The Pioneer's radioactive power sources, known as RTGs, emitted warmth unevenly, and that thermal radiation acted like a faint but constant push against the probe's direction of travel. Yet, even after accounting for thermal recoil, tiny discrepancies remained just enough to keep the door cracked open for alternative explanations. Could there still be an undiscovered force at play? Some researchers note that other distant spacecraft, like New Horizons, haven't shown the same effect, complicating the picture. Others point out that if thermal radiation fully explained the anomaly, why did it match the Pioneer's spin rate so eerily? What makes the Pioneer anomaly so fascinating isn't just the science, it's what it teaches us about how we explore the unknown. Sometimes, the universe's greatest mysteries turn out to have mundane answers. But those answers often lead to new questions, proving that even in the quiet reaches of space, there's always another layer to uncover. The Pioneers may have solved their own riddle, but their legacy endures as a reminder. The smallest anomalies can sometimes point to the biggest truths. In October 2017, astronomers spotted something streaking through our solar system that shouldn't have been there. A tiny, faint object moving so fast it could only have come from beyond our sun. They named it Oumuamua, Hawaiian for scout or messenger from afar. And at first, it seemed like a run-of-the-mill interstellar visitor, the first ever confirmed. But the closer scientists looked, the stranger it became. Its speed wasn't the weird part, it was how it accelerated as it raced away from the sun, as if something was pushing it. Comets do this sometimes, venting gas and dust as they heat up, creating a natural thruster effect. But Oumuamua showed no coma, the fuzzy glow of evaporating ice, and no visible tail. If it was a comet, it was the most bizarre one we'd ever seen. Then there was its shape. Based on how its brightness flickered as it tumbled, researchers concluded it was either cigar-shaped, stretched out to 10 times its width, or pancake flat. Either way, nothing in our solar system looks like that. Asteroids are lumpy and irregular, not sleek and elongated. So what was it? The mystery deepened when Harvard astronomer Avi Loeb proposed a radical idea. Maybe Oumuamua wasn't natural at all. Its acceleration, he argued, matched what you'd expect from a thin, lightweight object pushed by sunlight, a solar sail, perhaps, like the ones we've designed for future space probes. The notion sparked fierce debate. Critics pointed out that Oumuamua's trajectory could be explained by outgassing we simply failed to detect, or that its shape might be an illusion caused by its unusual rotation. But Loeb held firm, suggesting we might have glimpsed discarded technology from another civilization. Then came the final twist. Just as telescopes turned to study it more closely, Oumuamua vanished into the darkness, too faint to track. We'll never get another look, and that's the heart of the mystery. Was it a fragment of a shattered planet, a cosmic iceberg venting invisible hydrogen, or something even more extraordinary? The universe sent us a visitor, gave us just enough to question everything, and left us with no answers, only possibilities. And that's what makes Oumuamua more than a curiosity. It's a reminder that the cosmos is full of surprises, and sometimes the most profound discoveries are the ones that slip away before we can understand them. Deep within the cosmic microwave background, the faint afterglow of the Big Bang, there's a patch of sky that refuses to play by the rules. Known as the cold spot, this region is significantly colder than its surroundings, a cosmic chill so pronounced that it defies standard explanations. At first glance, it might seem like a minor statistical fluke in the universe's thermal fingerprint. But when astronomers calculated the odds of something this extreme occurring randomly, the numbers were staggering, less than 1 in 50,000. This isn't just background noise, it's a full-blown anomaly that's forced scientists to rethink some of their deepest assumptions about the cosmos. One leading theory suggests the cold spot might be the ghostly imprint of a supervoid, an enormous, underdense region of space where galaxies are eerily scarce. The logic goes like this: as light travels through such a void, it loses energy climbing out of the gravitational well, a process called the integrated Sachs-Wolfe effect. The result, a slight cooling in the CMB, like a shadow cast by cosmic emptiness. But here's the catch: the void required to explain the cold spot would need to be mind-bogglingly vast, over 1 billion light-years across. Surveys have found underdense regions nearby, but nothing on that scale. If it exists, it's either hidden or so colossal that it rewrites our understanding of large-scale cosmic structures. Then there's the more radical possibility that the cold spot is evidence of a collision with another universe. In the multiverse scenario, where countless bubble universes pop into existence beyond our own, two such bubbles might occasionally brush against each other. The energy release from such a collision could leave a distinct circular imprint in the CMB, exactly the kind of anomaly we see in the cold spot. It's a breathtaking idea, suggesting we might be staring at the first observational evidence of a parallel cosmos. But critics point out that the spot's shape isn't perfectly circular, and alternative explanations, like exotic physics in the early universe, can't yet be ruled out. The irony: the cold spot's greatest significance might not lie in which theory is correct, but in how it exposes the limits of our cosmic knowledge. Whether it's a record-breaking void, a bruise from another universe, or something even stranger, this icy anomaly reminds us that the universe still holds mysteries too big for our current models. Every time we map the cosmos, we're not just charting the known, we're uncovering the edges of our understanding, where the real discoveries begin. We think we know what the universe is made of: protons, neutrons, electrons, all the familiar stuff that builds planets, stars, and even us. But here's the thing: when astronomers tally up all the visible matter in the cosmos, nearly half of it is missing. This isn't dark matter, this is ordinary matter, the kind we're made of, technically called baryonic matter. And according to our best models of the Big Bang, it should be everywhere. So where did it all go? The numbers don't lie. Based on the cosmic microwave background and the universe's early chemistry, scientists can calculate exactly how many baryons should exist today. Yet when they count up all the stars, galaxies, and gas clouds we can see, they come up startlingly short, about 40 to 50% less than predicted. It's like meticulously balancing your checkbook, only to find half your paycheck vanished without a trace. The question isn't just academic. If we're missing something this fundamental, it means our understanding of cosmic structure has a glaring blind spot. So where could these baryons be hiding? One leading theory points to the vast, invisible webs of hot gas strung between galaxies. Picture the universe as a sponge, with galaxies clustered in the dense knots and threads, while the spaces between are soaked with diffuse million-degree plasma. This gas is so hot it emits X-rays rather than visible light, making it nearly transparent to traditional telescopes. But with X-ray observatories like Chandra, astronomers have begun detecting these faint filaments, confirming they're packed with missing baryons, just in a form we couldn't see before. Then there's the intergalactic medium, the even sparser gas filling the voids between galaxy clusters. Simulations suggest this might be the ultimate baryon reservoir, with atoms stretched so thin they're practically ghosts. Detecting them requires quirks of physics, like how their slight absorption alters the light of distant quasars, but even that only accounts for part of the deficit. Some researchers argue the answer lies closer to home, with baryons hiding in plain sight as rogue planets, failed stars, or cold gas clouds drifting unseen in our galactic neighborhood. Others propose more exotic ideas, like primordial black holes formed in the early universe, swallowing baryons before they could light up the sky, the most tantalizing clue. Some of this missing matter might not be missing at all, just misplaced. Galaxies eject staggering amounts of gas through supernova explosions and black hole winds, flinging baryons into deep space where they're nearly impossible to track. Over billions of years, this cosmic redistribution could have scattered matter far beyond where we've bothered to look. What makes this puzzle so profound isn't just the mystery, it's the humility it demands. We're literally made of baryons, yet we can't account for half of them in the universe. It's a stark reminder that even the most ordinary ingredients of reality can defy our expectations, hiding in the shadows until we learn to see them differently. And until we do, the universe's ledger will remain tantalizingly unbalanced. Out in the constellation Monoceros, some 2,300 light-years from Earth, there's a cosmic structure so geometrically perfect, it looks like it was drawn with a ruler, the Red Rectangle Nebula. Most nebulas billow and swirl like smoke, but this one defies the chaos with its sharp, symmetrical X-shape, framed by glowing red gas that gives it its name. What could possibly sculpt something so precise in the messy vastness of space? The answer lies in a dance of death between two stars locked in a gravitational embrace. At the heart of the red rectangle sits a binary star system, HD 44179, where an aging red giant and a smaller, hotter companion whip around each other in a tight orbit. As the red giant nears the end of its life, it sheds layers of gas and dust in a slow, stellar exhale. Normally, this material would puff outward in all directions, forming a spherical shell. But here's where the binary duo works its magic. Their orbital motion acts like a cosmic egg beater, flinging the ejected gas into two opposing cones. From our vantage point, those cones overlap to create the illusion of an X, with the star's light reflecting off dust grains to paint the nebula its eerie crimson hue. The real mystery isn't just the shape, it's the scale. The red rectangle's arms stretch nearly a third of a light year, far larger than most binary-influenced nebulas. Some scientists think the system might have experienced periodic outbursts, ejecting material in pulses that amplified the structure over millennia. Others point to the nebula's bizarre chemistry. It's packed with complex organic molecules like anthracene and pyrene, compounds more commonly found in coal tar than in space. These molecules fluoresce under ultraviolet light, intensifying the nebula's red glow and hinting at processes we don't fully understand. What makes the red rectangle truly special is how rare it is. For decades, it stood alone as the only nebula of its kind, until astronomers began spotting similar X-shaped structures around other binary systems. Each one is a cosmic fingerprint, revealing how stellar partnerships can twist chaos into order. But even among these, the red rectangle remains the most striking, a testament to the universe's ability to craft perfection from the most violent of dances. And as the stars at its center inch closer to their final act, likely collapsing into a white dwarf and triggering a planetary nebula, we're left to wonder, what other shapes might the cosmos carve when we're not looking? Saturn's north pole looks like it was plucked straight from a sci-fi novel because there, spinning in perfect symmetry, is a hexagon. Not a rough approximation, not a blurry maybe, but a near geometric six-sided storm so precise it could have been etched by some cosmic draftsman. Spanning nearly 20,000 miles across, wide enough to fit two Earths side by side, this atmospheric oddity has raged for at least 4 decades, possibly much longer, defying every expectation of how planetary weather should behave. So how does a hexagon, a shape more at home in a beehive than a gas giant, form in the turbulent chaos of Saturn's atmosphere? The answer lies in the planet's dizzying rotation. Saturn spins so fast a day there lasts just 10.5 hours, whipping its atmosphere into a frenzy of jet streams. One particularly stubborn current, racing at over 200 miles per hour, seems to act like an invisible barrier, shearing the turbulent gases into this bizarre polygon. Imagine stirring a cup of coffee with a spoon. If you spin it just right, you'll see geometric patterns form in the vortices. Saturn's hexagon might be the universe's most dramatic version of that experiment, scaled up to planetary proportions. But the real mystery isn't just the shape, it's the stability. Earth's hurricanes dissolve within weeks, yet Saturn's hexagon has outlasted every telescope pointed at it since Voyager first spotted it in the 1980s. Some scientists think the answer lies deep beneath the clouds, where differences in atmospheric density might act like an anchor, locking the storm in place. Others point to the hexagon's eerie stillness at its center, where winds are nearly calm, as if the storm is somehow self-reinforcing, a cosmic feedback loop we don't yet understand. And then there's the color. During Saturn's northern winter, the hexagon glowed a muted gold, but as summer approached, it shifted to a haunting blue, a change tied to chemical reactions in the atmosphere as sunlight returned. It's a reminder that this isn't just a static shape, it's a living, breathing weather system as dynamic as it is precise, the hexagon's most tantalizing clue. Similar shapes have been recreated in lab experiments with spinning fluids, suggesting it's not just a fluke, it's physics pushed to extremes, yet no model fully explains why only Saturn has this feature or why it's so freakishly enduring. For now, the hexagon remains a celestial paradox, a structure so orderly it seems almost artificial, carved into the clouds by forces we're only beginning to decode. And every time we gaze at it, we're reminded that nature's rulebook is far stranger and far more beautiful than we ever imagined. The moon today is a silent, airless world with no global magnetic field, yet hidden in its ancient rocks lies evidence of a dramatic past. Billions of years ago, our lunar neighbor once crackled with a magnetic field as strong as Earth's, a discovery that upended everything we thought we knew about how planetary magnetism works. For something as small as the moon to generate such a powerful field defies the usual rules after all. Magnetism typically requires a churning, molten metal core, and a body as modest as the moon should have cooled and solidified too quickly to sustain one. So how did it pull off this cosmic sleight of hand? The answer might lie in a gravitational tug of war with Earth. In its youth, the moon orbited much closer to our planet, and the intense tidal forces stretching its interior could have kept its core simmering far longer than expected. Picture squeezing a stress ball over and over. The friction generates heat. Similarly, Earth's gravity may have needed the moon's insides, stirring its molten iron core like a dynamo and sustaining that vanished magnetic shield. Some models even suggest the moon's core once spun at a different speed than its outer layers, creating a swirling conductive fluid that acted like a natural power generator. But the real mystery isn't just how the field existed, it's why it vanished. Around 1 billion years after the moon formed, the magnetic traces in lunar rocks suddenly drop off as if someone flipped a switch. The most likely culprit, distance. As the moon slowly drifted away from Earth, tidal heating waned, and without that energy, the core began to cool and solidify layer by layer, snuffing out the magnetic dynamo. Yet not everyone's convinced. Some researchers argue the field's collapse was too abrupt for simple cooling alone, proposing catastrophic events like a massive impact that disrupted the core's flow, or even the crystallization of a lighter mineral at the core's boundary, halting convection like a lid on a pot. The Moon's magnetic past isn't just a lunar curiosity, it's a window into planetary evolution everywhere. If something as small as the Moon could sustain a robust field, it raises tantalizing questions about other rocky worlds, from Mercury to distant exoplanets. Could magnetic fields come and go in planetary lifetimes, flickering on when conditions align and fading when the cosmic dance changes? Every sample from the Moon's surface carries tiny magnetic fingerprints, clues to a time when our silent companion was anything but inert, a world alive with unseen forces now frozen in stone. Venus, shrouded in thick clouds of sulfuric acid, might seem like the last place you'd expect a storm, let alone one that behaves like nothing else in the solar system. But hovering over its south pole is a freak of atmospheric mechanics. A swirling, double-eyed vortex larger than Europe, spinning like a pair of cosmic hurricanes locked in an endless dance. This isn't just any storm, it's a structure so bizarre, it makes Saturn's hexagon look downright ordinary. The first hints of this anomaly came when the European Space Agency's Venus Express probe arrived in 2006. Expecting chaotic turbulence, scientists instead spotted a vast hurricane-like spiral with not one but two distinct centers, a configuration never seen on any other planet. The vortex stretches over 1,200 miles wide, yet it's eerily stable, maintaining its twin-eyed shape for years at a time despite Venus's hellishly fast winds, which whip around the planet at over 200 miles per hour. Normally, atmospheric vortices merge or collapse under such chaos, yet this one stubbornly refuses to follow the rules. So how does such a freak of nature form? Venus's atmosphere is a nightmare of extreme super-rotating, meaning its upper winds circle the planet in just 4 Earth days while the surface barely moves. This creates a colossal shear effect, like two giant conveyor belts sliding past each other. At the poles where these forces collide, the spinning air gets funneled into towering waves, twisting into a vortex. But the double eye, that's where things get weird. Some models suggest it's caused by unstable atmospheric waves bouncing between the pole and equator, creating interference patterns that split the vortex like a reflection in a funhouse mirror. Others argue it's a side effect of Venus's odd polar dipole, a pair of high-pressure zones that act like atmospheric traffic cops, forcing the storm into symmetry. The real mystery isn't just its shape, though. It's the vortex's cold heart. Unlike Earth's hurricanes fueled by warm ocean water, Venus's vortex is coldest at its core, a phenomenon that flips meteorology textbooks on their heads. Some researchers think this chilling effect comes from gases rising and adiabatically cooling like a cosmic refrigerator. But why it stays so organized and why it doesn't dissipate remains one of planetary science's most stubborn puzzles. What makes this vortex so captivating isn't just its defiance of physics, it's what it reveals about how little we know. Venus, often called Earth's twin, has an atmosphere that operates like an alien laboratory where familiar rules twist into something unrecognizable. Every time we study this swirling enigma, we're reminded that even in our own cosmic backyard, nature still has tricks up its sleeve, and some of them come with 2 eyes. Mars should be a geologically quiet world, no active volcanoes, no shifting tectonic plates, just a frozen desert where nothing much changes. Yet something on the red planet is breathing. Over the past 2 decades, multiple missions have detected sudden, unexplained bursts of methane gas in the Martian atmosphere, some so concentrated they spiked to levels comparable to Earth's methane-rich regions. The catch: methane shouldn't last long in Mars's thin air. Solar radiation and chemical reactions break it down within a few hundred years, meaning whatever's releasing it must be doing so right now. And that raises the billion-dollar question. Is this gas coming from living microbes beneath the surface, or is there some geological process we've yet to understand? The first whiff of this mystery came in 2003, when the European Space Agency's Mars Express orbiter caught traces of methane hovering over specific regions. Then, in 2013, NASA Curiosity rover did something unprecedented. It sniffed out a tenfold spike in methane right at ground level in Gale Crater, lasting just weeks before vanishing. These aren't faint background traces, they're localized transient plumes like puffs of smoke from an unseen source. Even stranger, some detections show seasonal patterns, ramping up in the Martian summer and fading in winter, as if something underground is cycling with the planet's temperature. So where's it coming from? On Earth, 95% of methane is biological, belched by microbes, rotting plants or livestock. That's why the discovery sent astrobiologists into a frenzy. If Martian microbes exist, they might be huddling in briny aquifers beneath the permafrost, metabolizing hydrogen or carbon dioxide and exhaling methane as a byproduct. But before we jump to aliens, geology offers alternatives. Serpentinization, a reaction between water, carbon dioxide, and certain minerals like olivine, can produce methane without life. The problem: Mars lacks the robust volcanic activity or hydrothermal systems that typically drive this process on Earth. The plot thickened in 2018 when the ESA's Trace gas orbiter, armed with the most sensitive instruments yet, found no methane in the global atmosphere. This contradiction isn't just a technical glitch. It suggests methane on Mars is both fleeting and hyperlocal, escaping detection unless you're in the right place at the exact right moment. Some researchers think the gas might be trapped in underground reservoirs, leaking out through cracks when temperatures rise or meteorites shake the ground. Others propose an even wilder idea. Methane clathrates ice like cages of water. Molecules that trap gas could be destabilizing abruptly, releasing ancient reservoirs in sudden bursts. The most tantalizing clue lies in the timing. Curiosity's spikes often coincide with nighttime on Mars, when the atmosphere is calm and any subterranean gas might rise undiluted. It's as if the planet is whispering secrets in the dark, only to clam up at dawn. Future missions like NASA Mars Life Explorer aim to drill deeper, hunting for isotopic fingerprints in the methane that could reveal its origin. If the gas is rich in carbon-12, a light isotope favored by living organisms, it might tip the scales toward biology. But if it's purely geological, that still reshapes our understanding of how a dead planet can hiccup to life. For now, Mars keeps its secrets. Every methane spike is a flare in the dark, hinting at processes we're only beginning to grasp. Whether it's the faint breath of hidden life or the groan of rocks reacting in ways we've never seen, one thing's certain: the red planet is far from silent. It's just speaking in a language we're still learning to decode. Beyond the orbit of Neptune, where the solar system fades into a twilight zone of icy debris, astronomers have stumbled upon a cosmic cliffhanger, the Kuiper Cliff. This abrupt boundary, roughly 50 astronomical units from the Sun, marks where the population of Kuiper Belt objects suddenly plummets, as if someone drew a line in the cosmic sand and told everything beyond it to vanish. It's not just a gradual thinning like the last stragglers at the edge of a crowd. This is a hard stop, a statistical anomaly so glaring, it defies the expected distribution of these frozen leftovers from the solar system's formation. The Kuiper Belt should, in theory, stretch on for hundreds of astronomical units, peppered with icy worlds like Pluto and its kin. Yet beyond 50O, the belt's density drops off a cliff, leaving scientists scrambling for explanations. One tantalizing possibility: an unseen planet, something massive enough to sweep the region clean of debris through sheer gravitational muscle. Dubbed Planet 9 by some researchers, this hypothetical world could be 10 times the mass of Earth, lurking hundreds of O away in a skewed orbit. Its gravitational tug might have shepherded Kuiper belt objects into clustered orbits while ejecting others entirely, carving out the mysterious void we see today. But not everyone's convinced. Alternative theories suggest the cliff might be a fossilized edge, a relic of the solar system's violent infancy. During the chaos of planetary migration, Neptune could have bulldozed outward, scattering most icy bodies inward while leaving the outer belt barren. Others propose a more dramatic scenario, a close encounter with a passing star in our sun's stellar nursery, stripping away the outer Kuiper belt like a thief in the night. The most puzzling detail, some objects have been spotted beyond the cliff, like Sedna, a dwarf planet with an orbit so stretched it loops out to nearly 1,000 O. How these outliers survived the purge only deepens the mystery. Are they stragglers from a larger population, or did something else sculpt their peculiar paths? Until we probe deeper into the solar system's frozen fringe, the Kuiper cliff remains a cosmic puzzle, one that might rewrite our understanding of how planetary systems evolve. Whether it's an unseen giant, a celestial heist, or a fossilized boundary, this abrupt edge whispers that our solar system story is far from fully told. And somewhere out there, in the darkness beyond Neptune, the answer might be waiting. Our galaxy isn't just a serene island of stars, it's a cosmic predator, slowly devouring its smaller neighbors in an act of gravitational cannibalism. The victim in this celestial feast, the Sagittarius dwarf galaxy, a faint, ancient structure that's been locked in a death spiral with the Milky Way for billions of years. Right now, as you read this, our galaxy's immense gravity is stretching Sagittarius into a shimmering ribbon of stars, wrapping it around us like a twisted celestial halo. The saga began over 4 billion years ago when this tiny galaxy, just 1/10,000th the Milky Way's mass, ventured too close. Like a spider caught in a web, Sagittarius found itself trapped, doomed to orbit our galaxy in progressively tighter loops. With each pass, the Milky Way's tidal forces peeled away stars and dark matter, scattering them into vast, looping streams that now encircle us. These stellar rivers, invisible to the naked eye, were only discovered in the 1990s when sensitive telescopes mapped the sky and revealed the ghostly remnants of Sagittarius disintegration, a cosmic crime scene written in starlight. What makes this destruction so fascinating isn't just its scale, but its impact on our own galaxy. Every time Sagittarius plunges through the Milky Way's disk, it sends gravitational shockwaves rippling through the gas and dust, triggering bursts of star formation. Some astronomers even suspect our solar system's birth, roughly 4.5 billion years ago, might have been nudged by one of these violent encounters. It's as if the Milky Way isn't just consuming Sagittarius, it's using its remains to fuel new creation. The dwarf galaxy's fate is sealed. Already reduced to a tattered core just 10,000 light-years across, Sagittarius will likely vanish entirely within the next 100 million years, its stars assimilated into the Milky Way's swirling arms. But its legacy lingers. By studying these stellar streams, scientists have uncovered clues about dark matter's distribution, revealing how our galaxy's invisible scaffolding guides the cannibalization process. Some models even suggest Sagittarius isn't alone. Dozens of other dwarf galaxies may have met similar fates, their stars now hiding in plain sight among our own. Here's the chilling twist: the Milky Way's predatory phase won't last forever. In about 4 billion years, we'll face our own devourer, the Andromeda Galaxy, in a collision that will reshape both galaxies forever. Sagittarius offers a preview of that future, a reminder that even galaxies aren't immortal. They grow, they feed, and someday they too will be consumed. For now, we're the hunters, not the hunted, but the universe has a way of balancing the scales. Right now, the Andromeda Galaxy hurtles toward us at 250,000 miles per hour, an inevitable cosmic crash that will rewrite the night sky forever. Despite the mind-boggling scale of this collision, the laws of physics have already locked in its fate. In roughly 4.5 billion years, the Milky Way and Andromeda, two titans each carrying hundreds of billions of stars, will begin a gravitational tango that lasts for eons, merging into a single colossal galaxy. But this isn't some chaotic demolition derby. It's a slow-motion ballet where the universe's emptiest spaces play a starring role. Picture the sheer vastness between stars. Even in the densest regions of our galaxy, the average distance between neighboring stars is about 4 light years, enough room to fit 30,000 solar systems side by side. When Andromeda plows through the Milky Way, direct star-on-star collisions will be vanishingly rare. Instead, gravity will sculpt both galaxies into bizarre, swirling shapes, stretching their spiral arms into tidal tails of scattered stars. Over millions of years, these distortions will grow more dramatic, like two pools of ink stirred together in water, until the galaxies lose their distinct identities entirely. What's truly wild is how different the sky will look during this process. As Andromeda approaches, it'll dominate the night sky, growing from a faint smudge to a blazing disk nearly 20 times wider than the full moon. Then, as the galaxies entwine, new star-forming regions will ignite like fireworks, their glow visible even in daylight. But here's the twist: Earth's night sky won't just gain stars, it'll lose them too. As the merger reshapes gravitational fields, our solar system could be flung outward into the galactic halo, leaving us adrift in a darker, lonelier pocket of the new supergalaxy. The aftermath might sound apocalyptic, but for the galaxies themselves, it's more like a rebirth. Simulations suggest the merged entity nicknamed Milkdromeda will likely take on an elliptical shape, a golden blob of stars without the elegant spirals we know today. Yet this isn't the end of the story. Recent studies hint that a third galaxy, the Triangulum Galaxy, might join the fray, turning this duel into a chaotic three-way merger. Humanity won't be around to witness this spectacle. Our sun will have long since ballooned into a red giant by then, but the merger's legacy could echo far into the future. The combined galaxy might become a beacon for hypothetical civilizations, its size and brightness standing out in a universe where galaxies are drifting ever farther apart. For now, Andromeda's approach serves as a humbling reminder. Even the mightiest structures in space are bound by gravity's slow, unrelenting pull, dancing to rhythms set in motion billions of years ago. Stretched across billions of light years, quasars should be pointing every which way, cosmic lighthouses flickering at random in the void. Yet when astronomers mapped over 100 of these ultra-bright galactic cores, they stumbled upon something eerie. Their rotation axes weren't just randomly tilted. They were lining up as if threaded on invisible strings stretching across nearly half the observable universe. This spine-chilling alignment, some quasars spinning in parallel over distances that defy logic, shouldn't exist. According to our best models, these supermassive black holes, each powering a quasar's furious glow, should spin in entirely uncorrelated directions. The scale of this coordination is so vast, it's like flipping a coin 1,000 times and getting heads every single time. What makes this discovery so unsettling is what it implies about structure in the cosmos. Quasars are separated by mind-boggling distances so far apart that no known force could synchronize them. Even gravity, the universe's architect, moves too slowly to orchestrate such alignment across billions of years. Some theorists suggest this might be evidence of primordial magnetic fields woven into the fabric of space-time during the Big Bang, gently nudging quasars into alignment as they formed. Others propose an even wilder idea, that the early universe wasn't perfectly uniform. Instead, it might have contained vast, rotating waves in space-time itself, cosmic whirlpools that imprinted a preferred spin direction on everything that followed. Then there's the dark matter angle. If dark matter isn't just an invisible cloud but has some subtle directional preference, like an unseen current flowing through the cosmos, it might have steered galaxies and their central black holes into this bizarre synchronization. But even this explanation struggles with the sheer scale of the alignment, stretching far beyond what any local influence could achieve, the most radical possibility. That we're seeing the fingerprints of something beyond our universe. In multiverse theories, collisions between bubble universes could leave imprints on cosmic structure, like bruises on an apple. If our universe once brushed against another, the resulting shock waves might have carved out preferential axes, guiding quasar spins like compass needles pointing to a forgotten collision. Yet for all the theories, one truth remains. The quasar alignment is a direct challenge to the cosmological principle, the bedrock idea that the universe is uniform in all directions. If this pattern holds, it means the cosmos isn't just lumpy on small scales. It might have a grain, a hidden directionality written into its bones. Every new survey deepens the mystery, revealing more quasars caught in this cosmic choreography. And with each discovery, we're forced to confront an unnerving question. Is the universe playing by rules we haven't even discovered yet? Somewhere in the depths of space, a cosmic monster is on the run, a supermassive black hole, billions of times the mass of our sun, fleeing its home galaxy at unimaginable speed. Hubble's sharp eye caught this rogue behemoth in the act, not just drifting through the void but blazing a trail of stellar chaos in its wake, stretching over 200,000 light-years, twice the width of our Milky Way. This bizarre streak of newborn stars shouldn't exist. Black holes are supposed to lurk at galactic centers, not go rogue across intergalactic space. Yet here it is, racing away at 4 million miles per hour, dragging a river of star formation behind it like a celestial graffiti artist. So how does something this massive get kicked out of its own galaxy? The leading theory reads like a cosmic crime scene. Billions of years ago, two galaxies likely collided, their central black holes spiraling toward each other in a gravitational dance. As they merged, a third black hole may have entered the fray, a chaotic trio where one got flung outward like a stone from a slingshot. Simulations show these three-body interactions can eject the smallest black hole at staggering speeds. But in rare cases, if two black holes merge just right, the resulting recoil from gravitational waves ripples in space-time itself, can launch even a supermassive black hole clear out of its galactic home. What's truly mind-blowing isn't just the black hole's escape, it's the trail it leaves behind. As the runaway plows through gas clouds in intergalactic space, it compresses and shocks the material, triggering a firestorm of star birth in its wake. Normally, such regions would take eons to form stars naturally, but this black hole's passage acts like a cosmic snowplow, piling up stellar fuel and igniting it in a frantic burst. The result, a luminous contrail of young, blue stars, some no older than a few million years, stretching far beyond any galaxy's reach. The discovery reshapes how we think about black holes' role in the cosmos. Instead of passive anchors at galactic hearts, they can be dynamic engines of creation, scattering seeds of light in the darkest voids. And if one supermassive black hole got ejected, how many others are out there, drifting unseen? Future telescopes, like the upcoming Nancy Grace Roman Space Telescope, could uncover more of these renegades, rewriting our understanding of how galaxies and their dark hearts evolve. For now, this runaway giant stands as a cosmic rebel, proving even the universe's most destructive forces can leave beauty in their wake. Imagine a world where the ground beneath your feet isn't rock or sand, it's diamond. Not just scattered gems, but a planet-sized crystal stretching from crust to core. That's the mind-bending reality of 55 Cancri E, an exoplanet orbiting a star 40 light-years away, where the very chemistry of creation might have forged one of the universe's most extravagant treasures. This isn't just a glittering hypothetical. 55 Cancri E's diamond potential comes straight from its astronomical recipe. The planet orbits so close to its sun-like host star that a year there lasts just 18 hours, baking its surface to a scorching 2,700 degrees Celsius. But it's what lies beneath that heat that fascinates scientists. the planet's parent star is unusually rich in carbon, an element that forms the backbone of diamonds. Under the crushing pressure of 55 Cancri's interior, where gravity squeezes matter like a cosmic vise, all that carbon could have crystallized into a lattice of diamond hundreds of miles thick. The real kicker, this planet might not just contain diamonds, it could be one. Models suggest its core might be a single, monstrous diamond larger than Earth itself, wrapped in layers of graphite and topped with a thin, scorched atmosphere. Picture a cosmic jewelry store where the centerpiece isn't a gemstone on display, but the entire store itself. Yet even this dazzling scenario has skeptics. Some researchers argue the planet's carbon might instead form carbides, rocky compounds like silicon carbide, creating a world more like an abrasive grinding wheel than a luxury gem. What makes 55 Cancri truly extraordinary isn't just its possible composition, it's the window it offers into planetary diversity. Most rocky planets, including Earth, are built from oxygen and silicon. But swap in carbon as the dominant element, and you get a radically different kind of world, one where mountains might be made of diamond, rivers could flow with molten graphite, and volcanoes might spew liquid gems. It's a stark reminder that the universe doesn't just recycle the same planetary blueprint, it experiments, crafting worlds from whatever materials are on hand. The ultimate twist, 55 Cancri might not be alone. Carbon-rich stars aren't rare, and where there's carbon, there's potential for more diamond worlds. Future telescopes could reveal an entire class of these crystalline planets, rewriting our cosmic taxonomy. For now, 55 Cancri stands as a glittering enigma, proof that even in the vastness of space, nature's creativity knows no bounds. Who needs sci-fi when the universe cooks up planets like this? Most stars don't survive a supernova. When their cores collapse, they either explode into oblivion or leave behind a dense neutron star or black hole. But occasionally, the universe throws us a curveball, a star that endures its own violent death, emerging from the ashes like a cosmic phoenix. Meet the zombie star, a bizarre stellar remnant left behind by a failed supernova known as Type Ix. Unlike its cataclysmic cousins, this half-dead, half-alive oddity somehow survives the explosion, stumbling through space as a scarred, smoldering wreck of its former self. How does a star cheat death like this? The secret lies in its unique explosive mechanism. Most supernovae occur when a white dwarf, the dense core of a dead star, steals so much material from a companion star that it reignites in a runaway thermonuclear blast, obliterating itself completely. But in a Type Ix event, the explosion isn't quite strong enough to tear the white dwarf apart. Instead, it detonates unevenly, like a firework with a dud fuse, leaving behind a mangled stellar core that keeps burning, albeit weakly. Imagine setting off a bomb inside a building, only for one wall to remain standing. That's essentially what's happening here. The aftermath is just as strange. These zombie stars aren't just damaged survivors, they're fundamentally altered. The explosion strips away layers of material, leaving behind a bizarre hybrid object, part white dwarf, part supernova remnant, that glows with a haunting ultraviolet light. Some might even be flung away at incredible speeds, sent wandering through the galaxy like ghosts of their former selves. The most famous example, supernova 2008 Ha, where astronomers witnessed a star dimming but not disappearing, its core still flickering years after the explosion. What makes these stellar zombies so fascinating isn't just their defiance of physics, it's what they reveal about the delicate balance of cosmic destruction. Most supernovae are all-or-nothing events, but Type Ix explosions exist in a murky middle ground, proving that even stellar death isn't always absolute. They're cosmic cautionary tales, showing us that sometimes the universe doesn't play by the rules we've written. And with every new zombie star discovered, we're forced to reconsider what we thought we knew about how stars live, die, and sometimes refuse to stay dead. Out in the cold, dark stretches between stars, there are worlds with no sunrise, no sunset, no sky, but an endless void. These are rogue planets, castaways drifting through the galaxy without a star to call home. Some were born that way, condensing like lone wolves from collapsing gas clouds too small to ignite into stars. Others were violently evicted from their solar systems, flung into the abyss by gravitational tugs of war with sibling planets or passing stars. And the numbers are staggering. Astronomers estimate there could be billions of these nomads in the Milky Way alone, outnumbering stars by as much as 20 to 1. Take the case of SIMP J01365663 plus 0934873, a rogue planet just 20 light-years away. At 12 times the mass of Jupiter, it barrels through space untethered, its surface a blistering 800 degrees Celsius from the heat of its violent birth. Yet what makes it truly bizarre is its magnetic field, powerful enough to generate shimmering auroras in its thin atmosphere, despite having no stellar wind to stir them. Instead, interactions with interstellar plasma or even a hidden moon might be fueling these ghostly lights, turning this orphaned world into a self-contained cosmic lantern. Then there's the mind-bending possibility of stealth life. Rogue planets aren't all frozen wastelands. Some, especially those with thick hydrogen atmospheres, could trap geothermal heat for billions of years. Beneath ice shields or in subsurface oceans, microbial life might cling to existence, fueled by hydrothermal vents or radioactive decay, an entire biosphere cut off from starlight, thriving in eternal darkness. It's a haunting thought. The most common habitat for life in the universe might not be Earth-like worlds, but these drifting outcasts invisible to our telescopes. Yet spotting them is like finding a needle in a galactic haystack. Without a host star's backlight, rogue planets emit only faint infrared glows from their cooling cores. New tools like the Nancy Grace Roman Space Telescope aim to hunt them using microlensing, waiting for their gravity to bend and magnify the light of distant stars, revealing their presence like cosmic footprints in the snow. Each detection peels back another layer of the mystery. How many were born alone? How many were exiled? And could one, right now, be sailing silently past our solar system unnoticed? The most unsettling revelation: our own solar system might have lost planets this way. Simulations suggest Jupiter and Saturn's gravitational dance could have ejected a fifth giant planet early in our history, a sibling world now wandering the void. If so, rogue planets aren't just celestial curiosities. They're ghosts of what might have been, reminding us that even the most stable-looking systems are just one cosmic shove away from chaos. Galaxies are supposed to grow up slowly, taking billions of years to settle into the elegant spirals and disks we see in the modern universe. But the universe loves breaking its own rules, because astronomers have spotted fully formed disk galaxies shining in the deep past at a time when they shouldn't exist. These cosmic anomalies appear just 1 to 2 billion years after the Big Bang, flaunting the same smooth, flat shapes as our Milky Way, despite being born in an era of chaos and collisions. According to our best models, galaxies this young should be messy, clumpy blobs still reeling from their violent formation. So how did these impossibly mature disks come to be? The traditional story of galaxy evolution reads like a cosmic coming-of-age tale. In the early universe, gravity pulled gas and dark matter into dense knots, forming the seeds of future galaxies. These proto-galaxies spent their youth in constant turmoil, merging, colliding, and devouring each other in a frenzied dance that should have left them anything but orderly. Only after multiple mergers and eons of internal settling did theorists expect them to flatten into the neat disks we recognize today. But the James Webb Space Telescope has shattered that timeline, capturing snapshots of pristine disk galaxies from an era when the universe was barely out of infancy. One standout, dubbed the Sparkler, flaunts symmetrical spiral arms and a defined central bulge at just 3 billion years old, far too soon for textbook formation. So what's the secret behind these precocious galaxies? One leading theory suggests they formed in unusually calm cosmic neighborhoods, pockets of the early universe where gas flowed smoothly into growing galaxies instead of crashing in violently. Without the disruptive influence of frequent mergers, these galactic infants could have settled into disks almost immediately, like a spinning drop of water naturally flattening into a perfect circle. Another possibility is that their dark matter halos, the invisible scaffolding that shapes galaxy growth, were oddly lump-free, allowing gas to distribute evenly from the start. But the plot thickens when you consider how these ancient disks move. Modern spiral galaxies rotate like whirlpools, with stars and gas tracing orderly orbits around the center. Yet some of these early disks spin too fast for their mass, defying gravitational expectations. This could mean their dark matter halos are packed differently, or that supermassive black holes at their cores injected extra energy, stabilizing them prematurely. There's even a radical idea that the early universe's higher gas density allowed disks to form quickly before mergers could disrupt them, like baking a perfect cake in a hotter oven. The implications stretch beyond just rewriting galactic timelines. If mature disks existed earlier than thought, it means stars and potentially planets had more time to form, raising the odds of early life in the cosmos. It also challenges our assumptions about dark matter's role in shaping galaxies. Every new discovery from telescopes like Webb peels back another layer of the mystery, revealing a universe that doesn't just follow a script, it improvises, creating order out of chaos in ways we're only beginning to grasp. And somewhere out there, these impossible galaxies keep spinning, silent witnesses to a cosmic story far stranger than we ever imagined. At the farthest edges of our cosmic maps, where the observable universe fades into mystery, something impossible is happening. Hundreds of galaxy clusters, each one a behemoth containing thousands of galaxies, are streaming toward a single point in space at speeds exceeding 2 million miles per hour. This isn't just random motion, it's a coordinated march toward an unseen attractor so distant, it lies beyond the cosmic horizon we can observe. Astronomers call it the dark flow, and its existence defies everything we know about how the universe should behave. The discovery came from painstaking observations of the cosmic microwave background, the afterglow of the Big Bang. As galaxy clusters race through space, their motion leaves a subtle fingerprint in this ancient light, a phenomenon called the kinematic Sunyaev-Zeldovich effect. When researchers analyzed data from hundreds of clusters, they found their velocities didn't cancel out as expected. Instead, they pointed like arrows toward a patch of sky between Centaurus and Vela, as if pulled by a gravitational force from outside our universe. The implications were staggering. Either our measurements were wildly wrong or something inconceivably massive, a structure or curvature of space-time beyond the observable cosmos, was tugging on everything. Critics argue it could be instrumental error or an unaccounted for local effect. But the dark flow persists across multiple datasets, including observations from the Planck satellite. What's unnerving is the scale. This flow extends over billions of light years, far beyond where any known structure should exert influence. The Great Attractor, a massive concentration of galaxies, can't explain it. Its pull is too weak and too close. This motion suggests a gravitational anomaly orders of magnitude larger, something so colossal it warps the fabric of space-time beyond our cosmic horizon. One radical explanation: the dark flow could be evidence of a neighboring universe brushing against our own in the multiverse. If another bubble universe exists infinitesimally close to ours, its gravity might leak through, creating a preferred direction in our cosmos. Alternatively, it might reveal that inflation, the rapid expansion of the early universe, left behind imprints we're only now detecting. Some theories even suggest our universe is unevenly curved on scales we can't yet measure, funneling matter toward an unseen cosmic slope. The most unsettling possibility that we're seeing the limits of the cosmological principle itself, the idea that the universe is uniform everywhere. If the dark flow is real, it means the universe might have a grain, a fundamental asymmetry written into its birth. Future telescopes could settle the debate by mapping galaxy motions in even deeper fields. Until then, this ghostly river of galaxies remains one of cosmology's greatest controversies, a current flowing toward answers we're not yet equipped to grasp. Black holes aren't just cosmic vacuum cleaners, they're messy eaters, and their dining habits leave behind some of the most dazzling graffiti in the universe. When a black hole tears into a star or devours a gas cloud, it doesn't just swallow everything silently. Instead, it creates a spectacular light show, bright rings of X-rays echoing through space like ripples from a stone tossed into a pond. These light echoes form when a black hole's feast sends out bursts of radiation, which then bounce off nearby clouds of gas and dust, creating concentric circles that expand outward at the speed of light. Take the black hole V404 Cygni, for example. In 2015, astronomers watched as it erupted in a violent feeding frenzy, blasting X-rays so intense they illuminated an entire nebula of ancient debris around it. But the real shock came when telescopes detected not just one flash, but multiple rings, each one marking a separate pulse of energy from the black hole's outburst. Like a cosmic strobe light, these flashes lit up different layers of surrounding gas, revealing structures invisible under normal conditions. The rings weren't just pretty, they were a forensic tool, letting scientists map the black hole's neighborhood in 3D for the first time. What makes these rings so valuable is what they tell us about black holes' chaotic appetites. The X-rays aren't emitted steadily, they come in erratic bursts, suggesting the black hole consumes its meals in fits and starts. Gas and dust don't spiral inward smoothly, they pile up in a turbulent disk, heating to millions of degrees until the pressure becomes too much, and the black hole belches out radiation like a cosmic volcano. Each ring's size and brightness act as a timestamp, helping astronomers reconstruct the black hole's outbursts down to the millisecond. But the wildest part, these echoes aren't just historical records, they're also shape-shifters. Over months or years, the rings expand, growing fainter, but also distorting as they encounter new pockets of interstellar material. Some rings even split into intricate sub-rings, like tree rings recording a drought, offering clues about long-ago collisions or supernova that littered the area with debris. In a way, black holes don't just consume, they illuminate, turning their violent meals into lanterns that reveal the hidden anatomy of the cosmos. The next time you picture a black hole, don't just imagine a dark abyss. Picture this brilliant, frenzied ring of fire, a testament to the fact that even destruction can light the way. Amid the swirling chaos of colliding galaxies and cosmic debris, there's one celestial oddity that stands out like a perfect bullseye in the void, Hoag's object. Discovered in 1950 by astronomer Art Hoag, this enigmatic ring galaxy floats some 600 million light-years away, defying every expectation of how galaxies should look. At its heart sits a serene, golden-yellow core of ancient stars, encircled by a near-perfect ring of younger, blue stars with nothing but darkness separating the two. No twisting spiral arms, no messy dust lanes, just a cosmic donut so symmetrical, it looks almost artificial. What makes Hoag's object so baffling isn't just its beauty, it's the mystery of how such a structure could form. Ring galaxies aren't unheard of, but they're usually the result of violent collisions where a smaller galaxy punches through the center of a larger one, sending shockwaves that trigger star formation in a ring. The Cartwheel Galaxy is a classic example, its spokes of dust and gas still ragged from the impact, but Hoag's object shows no signs of a recent collision. No debris, no distortion, just that pristine, gaping void between core and ring. It's as if someone carefully cut out the center of a galaxy and replaced it with another, leaving no fingerprints behind. One theory suggests it might be the remnants of an ancient bar, a straight line of stars that once stretched across the galaxy's center. Over time, gravitational instabilities could have caused the bar to dissolve, its stars migrating inward while gas and dust were flung outward, forming the ring. But simulations struggle to recreate Hoag's object's flawless symmetry. Real galaxies are messy, with lopsided ripples and clumps. Another idea points to accretion, the slow, steady capture of gas from intergalactic space, settling into a ring and igniting new stars. Yet even that doesn't fully explain the eerie emptiness between the core and the ring. The plot thickens when you peer deeper into the darkness. In 2002, astronomers spotted another, fainter ring galaxy lurking behind Hoag's object, a cosmic doppelganger just as mysterious. Could this be a clue that such structures form under rare, specific conditions? Or is it pure chance, a trick of perspective? Even more bizarre, some researchers have proposed that Hoag's object might be the result of an instability cascade, where waves of star birth and death propagated outward in perfect harmony, leaving behind this celestial artifact. The most tantalizing question of all, is Hoag's object a galactic anomaly, or are there more of these perfect rings hiding in plain sight? Modern telescopes, with their ability to peer through dust and scan vast swaths of sky, have turned up a handful of similar galaxies, each as puzzling as the last. They're reminders that the universe delights in breaking molds, crafting objects that defy our neat classifications. Hoag's object isn't just a pretty oddity, it's a challenge, a cosmic riddle scribbled in starlight, waiting for us to unravel its secrets. In the heart of the Tarantula Nebula, a sprawling stellar nursery 160,000 light-years away, there are explosions so powerful they don't just light up the cosmos, they carve it. Meet the superbubbles, colossal cavities stretching hundreds of light-years across, where the combined fury of young stars and dying giants has blown a hole straight through the nebula's gas clouds. These aren't just empty spaces, they're cosmic demolition sites where the winds of countless stars collide in a dazzling display of raw energy, sculpting the nebula into a labyrinth of glowing filaments and cavernous voids. The violence begins with the nebulous star clusters, crowded metropolises of massive, short-lived stars. Each of these blue giants burns millions of times brighter than our sun, blasting out supersonic stellar winds at speeds exceeding 10 million miles per hour. Imagine standing in a hurricane, then multiply that by 1 billion. That's the force these winds exert, pushing against the surrounding gas like invisible plows. But the real fireworks start when the biggest stars reach the end of their lives, detonating as supernovae so powerful, their shockwaves can travel for centuries, compressing gas into new stars even as they obliterate the old landscape. The result, a chain reaction of destruction and creation. Take the superbubble LMC4, a gaping hole in the Tarantula Nebula's fabric. Spanning over 1,000 light-years, it's the work of multiple supernova and stellar winds piling up over millions of years, like cosmic construction crews clearing a mega highway through interstellar space. X-ray telescopes reveal the walls of these bubbles glowing at temperatures of several million degrees, heated by the relentless bombardment of high-energy particles. Yet within these chaotic shells, something magical happens. The compressed gas at their edges collapses into dense knots, igniting the birth of even more stars. It's a stellar paradox. The same forces that tear the nebula apart also seed its future. What makes these structures so mesmerizing is how they defy simple physics. Superbubbles don't expand uniformly. They twist and warp as they plow through regions of varying density, creating intricate shapes that resemble cosmic fingerprints. Some develop secondary bubbles within bubbles, like Russian nesting dolls of destruction, while others blow out entirely, venting their hot gas into intergalactic space. The tarantula's most famous example, 30 Doradus, is so turbulent that astronomers have nicknamed it the cosmic hurricane, a maelstrom where supersonic winds collide to create towering shock fronts, visible in radio waves as rippling curtains of energy. But the real surprise, these superbubbles might hold clues to one of astronomy's biggest mysteries: how galaxies regulate their star formation. Without these violent outbursts, galaxies could choke on their own gas, forming stars so rapidly they'd burn out in a cosmic blink. Superbubbles act like pressure valves, venting energy and metals forged in supernova into the wider universe, enriching future generations of stars and planets. In a way, the tarantula's chaos isn't just destruction, it's a vital part of the universe's life cycle, proving that even in the darkest corners of space, there's a delicate balance between chaos and creation. And every time we peer into these stellar battlegrounds, we're witnessing the engines that shape galaxies themselves. Deep in the asteroid belt between Mars and Jupiter, a cosmic misfit wanders the solar system, Elst Pizarro, an object so bizarre it forces astronomers to rewrite definitions. At first glance, it's just another asteroid tracing a quiet elliptical path around the Sun like its rocky neighbors. But every now and then, this enigma wakes up, sprouting a glowing tail of dust and gas like a comet on cue. It's a celestial schizophrenic, blurring the line between two worlds that should never overlap, flaunting asteroid behavior one moment, comet theatrics the next. The mystery begins with its orbit. Unlike comets, which typically hail from the frozen reaches of the outer solar system and follow stretched elliptical paths, Elst Pizarro circles snugly within the asteroid belt, a region where temperatures should keep any ice locked in permanent hibernation. Yet somehow, whenever this object reaches its closest approach to the Sun, it defies expectations. In 1996, observers caught their first glimpse of its transformation, a ghostly tail stretching thousands of miles behind it, unmistakably comet-like. Since then, it's repeated the performance multiple times, spewing material in bursts that last weeks or months before fading back into asteroidal obscurity. So how does a rock in this cosmic neighborhood suddenly turn into a makeshift comet? The leading theory points to hidden reservoirs of subsurface ice. Unlike most asteroids, which are baked dry over billions of years, Elst Pizarro might harbor pockets of water ice buried beneath an insulating layer of dust. When sunlight heats its surface just enough during perihelion, that ice could vaporize violently, erupting through cracks in the crust and dragging dust along for the ride. Imagine a frozen lake buried under a desert, then suddenly, the heat punches through and geysers blast skyward. That's the kind of drama unfolding on this tiny world. But here's the twist: Elst Pizarro isn't alone. Astronomers have since identified a growing list of active asteroids, objects that straddle the same awkward divide. Some, like 323 Phaethon, spew dust when fractured by solar heat, creating the annual Geminid meteor shower. Others, like 133P/Elst Pizarro, yes, it's been reclassified so often it has multiple names, might be true hybrids, icy relics from the solar system's chaotic past that somehow ended up in the wrong neighborhood. What makes these objects so revolutionary isn't just their identity crisis, it's what they reveal about the solar system's early days. The asteroid belt wasn't always the orderly, ice-free zone we see today. Billions of years ago, these rocks might have formed much farther out, rich with volatile materials before gravitational shuffles dragged them inward. Elst Pizarro could be a fossil from that era, a time capsule proving water and rock mingled in places we never expected. The implications ripple beyond classification debates. If ice lurks undetected in more asteroids, it could rewrite the story of how water arrived on Earth, not just via comets, but through stealthy, ice-packed rocks bombarding our young planet. Future space miners eyeing asteroid resources might find more than just metals. They could stumble upon caches of cosmic ice ripe for harvesting. And for scientists, every outburst from Elst Pizarro is a chance to study comet-like processes up close without waiting for a rare visit from a true comet. Yet the biggest lesson here is about the universe's refusal to fit into neat boxes. Just when we think we've mapped the rules, nature hands us an exception, a rock that thinks it's a comet, a belt dweller with outer system secrets. Elst Pizarro isn't just an oddity. It's a reminder that the cosmos thrives on blurring boundaries, and the most fascinating discoveries often lie in the gray areas between what we think we know. Some stars don't get the explosive send-off they deserve, they just disappear. Imagine a massive star 20 times heftier than our Sun, burning bright for millions of years, only to vanish without so much as a cosmic firework. Astronomers call these cosmic no-shows failed supernova, and they're rewriting the rules of how stars die. Take N6946, a red supergiant in the fireworks galaxy that should have lit up the night sky with a supernova visible to the naked eye. Instead, between 2009 and 2015, it simply faded from view as if someone switched off a lamp. No brilliant flash, no shockwave, just silence. The most likely explanation: the star's core collapsed straight into a black hole, swallowing the explosion before it could even begin. Picture a building imploding inward so fast the dynamite never gets a chance to detonate. That's the fate of these stars. Their own gravity turns traitor, cutting short their final act. The mechanics behind this stellar disappearance are as brutal as they are fascinating. Normally, when a massive star exhausts its fuel, its core collapses, rebounding in a cataclysmic supernova that blasts the outer layers into space. But in some cases, the collapse doesn't stop. If the star is massive enough, or spinning just right, the core might bypass the explosion entirely, condensing directly into a black hole with such speed and efficiency that the overlying star material gets sucked down like water down a drain. The result, a star that winks out of existence, leaving behind only a faint infrared glow as its outer layers spiral into the newborn black hole's maw. This isn't just a quirky one-off. Surveys like the Large Binocular Telescope's Vanishing and Appearing Sources project have flagged dozens of candidate stars that pulled similar vanishing acts. Some might have been obscured by dust, but others defy conventional explanations. One theory suggests these stars could be cloaked in thick cocoons of material ejected in their death throes, muffling the explosion. Another posits that neutrinos, tiny, ghostly particles normally responsible for carrying away a supernova's energy, might instead get trapped by dense matter, robbing the explosion of its punch. The implications ripple far beyond stellar astronomy. If stars routinely vanish without supernova, it could mean we've underestimated the number of black holes lurking in our galaxy. It also solves a long-standing puzzle: why some supernova simulations fizzle out in supercomputers, collapsing into black holes before the explosion can take hold. Nature, it seems, has been running its own version of these failed experiments for eons. What's most haunting is the thought that somewhere out there, right now, a giant star might be meeting its quiet end. No fanfare, no spectacle, just the universe's darkest pit opening beneath it. These ghostly exits remind us that even in death, stars don't always follow the script, and every time one disappears without a trace, it's a humbling lesson. The cosmos keeps its most dramatic secrets hidden in the void. For over a century, starlight passing through the cosmos has carried cryptic messages, dark fingerprints smudged across its rainbow spectrum that no one can decipher. These are the diffuse interstellar bands, or DIB, hundreds of faint absorption lines where something in the vast spaces between stars has stolen specific wavelengths of light. Unlike the sharp spectral signatures of familiar atoms and simple molecules, DIBs are broad, fuzzy, and stubbornly resistant to identification. They're cosmic hieroglyphics written in a language we're still struggling to translate, potentially holding clues to some of the universe's most complex chemistry. The mystery began in 1922 when astronomer Mary Lee Hedger first noticed these odd lines while studying distant binary stars. At first, scientists assumed they'd pinned down the culprit quickly. After all, by matching absorption patterns to lab experiments, they'd already identified many interstellar molecules. But as decades passed and more DIBs were catalogued, the puzzle only deepened. Today, we've mapped over 500 of these bands, stretching from ultraviolet to infrared wavelengths, yet not a single one has been definitively linked to a known substance. What makes these spectral ghosts so baffling is what they reveal and conceal about their origins. The widths of the bands suggest they're created by large, complex molecules rather than simple atoms. Some researchers think they're seeing the fingerprints of carbon-based compounds called polycyclic aromatic hydrocarbons, PAR-flat, snowflake-like structures that could form in the sooty aftermath of dying stars. Others propose they're caused by even more exotic carbon chains, like Buckminster-Fullerene soccer ball-shaped C60 molecules or sprawling networks of linked atoms resembling interstellar graphene. But here's where things get truly strange. Many DIBs appear strongest in environments hostile to complex molecules, regions bathed in harsh ultraviolet radiation that should shred delicate molecular structures. This paradox has led to wilder theories, like the idea that these molecules might be shielded inside microscopic cages of ice or dust, or that they're not molecules at all, but some unknown form of quantum-scale structures behaving in ways laboratory chemistry can't yet replicate. The hunt for answers isn't just academic. DIBs could be the missing link in understanding how the building blocks of life spread through the galaxy. Many of the proposed molecules are rich in carbon, the same element that forms the backbone of DNA and protein. If these compounds are as abundant as DIBs suggest, they might serve as cosmic stepping stones, ferrying probiotic chemistry from star-forming regions to newborn planets. Yet for all their potential significance, DIBs remain maddeningly elusive. Modern telescopes like the Very Large Telescope in Chile have begun mapping their distribution across the Milky Way, revealing patterns that hint at multiple carriers rather than a single culprit. Laboratory scientists, meanwhile, race to recreate possible DIB-generating molecules in conditions mimicking interstellar space, hoping to catch a spectral match. It's a painstaking process, like reconstructing a symphony by listening for individual notes through static. What's most humbling about DIBs is how they expose the limits of our cosmic literacy. After centuries of decoding starlight, we're still surrounded by signals we can't interpret, written in compounds we've never seen. Every unexplained absorption line is a reminder that the universe's chemistry set is far more intricate than we imagined. And somewhere in those dark bands between the stars, nature might be crafting substances beyond our wildest conjectures. Until we crack their code, DIBs will keep whispering their secrets just beyond our grasp, turning the empty spaces between stars into one of astronomy's most tantalizing frontiers. When NASA Opportunity rover rolled across the rusty plains of Meridiani Planum in 2004, its cameras caught something unexpected: thousands of tiny, round stones littering the ground like spilled blueberries. These peculiar spherules, no larger than pebbles, weren't just geological curiosities. They were time capsules holding secrets from Mars's distant, watery past. Unlike the jagged rocks around them, these blueberries were nearly perfect spheres, their smooth surfaces hinting at a formation process far gentler than the violent impacts that usually shape Martian terrain. Analysis revealed they were made of hematite, an iron-rich mineral that on Earth often forms in the presence of liquid water. The rover's instruments detected something even more telling. The blueberries weren't scattered randomly but embedded in layers of sedimentary rock like fossils in a geologic textbook. This was the smoking gun, proof that water had once percolated through these rocks, dissolving iron and redepositing it in these spherical concretions over millions of years. The real revelation came when scientists compared them to similar formations on Earth. In places like Utah's Navajo sandstone or the hot springs of Japan, hematite spherules form when mineral-rich water flows through porous rock, gradually building up concentric layers around a central nucleus, a process akin to how pearls grow in oysters. On Mars, the blueberry's uniformity suggested sustained water activity, possibly in a shallow sea or groundwater system that persisted long enough for these tiny time capsules to grow. Some even showed microscopic dimples, likely where water once pooled before evaporating into the thin Martian air, but the blueberries weren't done surprising us. Later missions found larger, more varied spherules, some golf ball-sized at Endeavour crater, others clustered like bunches of grapes. Curiosity rover discovered different mineral compositions, not just hematite but also silica-rich spheres in Gale crater, hinting at diverse watery environments across Mars. Each variation adds another piece to the puzzle, perhaps some formed in acidic lakes, others in neutral pH groundwater, painting a portrait of a planet where water chemistry shifted over time. The most tantalizing question, whether these iron-rich spheres could preserve traces of ancient Martian life. On Earth, similar concretions have been found to encapsulate organic material, tiny biological time capsules. While no definitive evidence exists yet, the blueberries serve as mineral markers, guiding future missions to the most promising sites where Mars's wet past might have harbored life. Every one of these unassuming spheres is a bead on the cosmic abacus, helping us tally the epochs when Mars wasn't just red, but blue with water and maybe, just maybe, alive. For planetary scientists, these tiny orbs are more than geological oddities. They're Rosetta Stones written in iron and stone. They whisper of a time when rain might have fallen on Martian hills, when rivers carved valleys now dust dry, and when the cosmos flirted with the idea of a second blue planet in our solar system. And as future rovers roll across alien deserts, they'll keep an eye out for more of these cosmic blueberries, each one a tiny messenger from an era when Mars was a world transformed. Saturn's moon Titan is a world of surreal contradictions, a place where familiar landscapes twist into something alien. Its lakes aren't filled with water but with liquid methane shimmering under a hazy orange sky. And on these eerie hydrocarbon seas, something even stranger happens. Islands appear and vanish like mirages, flickering into existence for days or weeks before dissolving without a trace. Scientists call them Titans, magic islands, and they might be the closest thing we've seen to a natural phenomenon defying the laws of earthly physics. The first hints of these phantom islands came from NASA Cassini probe, which spent over a decade studying Saturn and its moons. Radar images of Titan's largest northern sea, Kraken Mare, revealed bright patches where none should exist, spots that weren't permanent landforms, yet weren't waves either. Some would vanish between flybys, only to reappear in different shapes weeks later. At first, researchers dismissed them as electronic noise or imaging artifacts. But as Cassini's observations piled up, the pattern became undeniable. Something was casting radar reflections on those methane lakes, something that moved. So what could these elusive islands be? One leading theory points to bubbles, not the delicate spheres we know on Earth, but massive plumes of nitrogen gas erupting from the lakebed. Titan's frigid temperatures, hovering around -180 degrees Celsius, allow nitrogen to dissolve into liquid methane like carbon dioxide in soda. When the lakes warm slightly, perhaps from seasonal changes or underground heat, the nitrogen could come fizzing out in explosive bursts, creating vast foamy patches that scatter radar signals before popping and vanishing. But bubbles might not be the only explanation. Another possibility: floating solids, hydrocarbon sludge clumping together like icebergs of organic goo. Titan's atmosphere constantly rains down complex hydrocarbons, forming dunes and plains of tar-like substances. Some of this material could clump into porous chunks light enough to float on methane's low surface tension, drifting until they either sink or dissolve. Imagine an iceberg, but instead of water ice, it's a spongy mass of frozen ethane and benzene, bobbing on a sea of liquid natural gas, the wildest twist. These islands might not just be floating, they could be moving. Titan's lakes experience tides from Saturn's gravity, and weak winds might push floating patches across vast distances. Radar data from one magic island showed its shifting position between observations as if carried by unseen currents. That raises an even more tantalizing prospect. Could these transient features be part of some larger hydrocarbon cycle, where solids form, float, and eventually break down only to reform elsewhere? What makes these phantom islands so mesmerizing isn't just their mystery, it's what they reveal about Titan as a living laboratory for alien chemistry. On Earth, we're used to water as the universal solvent, but here's a world where methane plays that role, crafting landscapes and phenomena we're only beginning to understand. Every flickering island is a clue, a fleeting glimpse into processes that might reshape how we think about liquids, solids, and the boundaries between them. And the stakes are higher than just solving a puzzle. If we ever send a probe to sail Titan's seas, a concept NASA has studied with proposals like the Titan Mare Explorer, these magic islands could be more than curiosities. They might be navigational hazards, scientific gold mines, or even stepping stones to uncovering Titan's potential for prebiotic chemistry. After all, the same carbon-rich molecules that might form these floating patches are the building blocks of life as we know it. For now, Titan's disappearing islands remain one of the solar system's most elegant enigmas, a reminder that even in the coldest, most alien corners of the cosmos, nature still has tricks up its sleeve. And every time one of these phantom features blinks in and out of existence, it's like the moon itself is teasing us, offering fleeting glimpses of secrets we're not yet ready to decode. Jupiter's moon, Europa, has long been one of the solar system's most tantalizing mysteries, a frozen world with a secret it just can't seem to keep. Hidden beneath its cracked, icy shell lies a global ocean containing more liquid water than all of Earth's seas combined. But Europa isn't content to hide its watery treasure. It broadcasts its secrets in spectacular fashion through towering plumes of water vapor that erupt into space like geysers from another world. The first hints came in 2012 when the Hubble Space Telescope spotted what looked like faint, transient clouds stretching over Europa's south pole. At first, scientists assumed it might be instrumentation error or some trick of the light. But when Hubble observed the same phenomenon again in 2016, this time catching ultraviolet signatures of water molecules being broken apart by Jupiter's intense radiation, there was no denying it. Europa wasn't just hiding an ocean, it was actively venting it into space, sending plumes soaring over 100 miles above its frozen surface. What makes these eruptions so extraordinary is what they imply about the moon's hidden plumbing. On Earth, geysers like Old Faithful are powered by geothermal heat boiling groundwater. Europa's plumes likely work similarly, but on a planetary scale, tidal forces from Jupiter's gravity constantly flex the moon's core, generating enough heat to keep the subsurface ocean liquid and occasionally fracture the icy ceiling above it. When these cracks reach pockets of pressurized water, the result is a violent decompression that fires vapor and ice crystals into the vacuum like a cosmic pressure cooker blowing its lid. The truly mind-bending part, these plumes might be delivering Europa's ocean water directly to us. When NASA Galileo probe flew through Europa's thin atmosphere in the 1990s, its instruments detected brief, unexplained spikes in plasma density, now suspected to have been whispers of these very plumes, brushing against the spacecraft decades before we knew to look for them. Future missions like Europa Clipper will carry mass spectrometers designed to fly through these towering jets, tasting their chemistry for signs of organic molecules or other hints that this dark ocean could harbor life. But the plumes aren't consistent. They flare up unpredictably, sometimes vanishing for years. Some researchers think they might be tied to Europa's orbital position, erupting when tidal stresses are greatest during its elliptical path around Jupiter. Others suggest they could be localized over hydrothermal vents on the ocean floor, where mineral-rich hotspots punch through the ice like underwater volcanoes. The implications are staggering. If we can sample these plumes, we're essentially getting free samples from an alien ocean without having to drill through miles of ice. Every molecule carries clues about the ocean's salinity, pH, and potential energy sources, all critical factors for habitability. There's even a chance these jets could contain microscopic life forms, frozen in the act of being ejected from their subterranean world. Of all the places beyond Earth where life might exist, Europa's plumes offer something unique, an invitation. Where Mars hides its secrets in dusty rocks and Titan's chemistry plays out behind a haze of hydrocarbons, Europa is practically shouting its potential into the void. These magnificent, intermittent fountains transform a distant ice moon into something visceral, a world that doesn't just harbor an ocean, but visibly, violently shares it with the cosmos. And as we prepare to send our robots to dance through these celestial geysers, we might be on the verge of the greatest discovery of all, that we're not alone in this vast, watery universe. Beneath Enceladus's icy crust, where sunlight never reaches and temperatures plunge hundreds of degrees below freezing, something extraordinary is happening. Hydrothermal vents towering chimneys of mineral-rich water are spewing superheated plumes into the moon's hidden ocean, creating an otherworldly oasis in the abyss. This isn't just a geological curiosity, it's a potential cradle for life, thriving in one of the most hostile environments imaginable. The discovery of these vents traces back to NASA's Cassini mission, which caught Enceladus in the act of erupting. Giant geysers of water vapor and ice were seen blasting from fractures near the moon's south pole, forming a shimmering plume that extended hundreds of miles into space. But the real revelation came when Cassini flew through those plumes and detected something unexpected: tiny grains of silica, so small they could only form in scorching water. The implication was staggering. Somewhere beneath that frozen shell, hot water was interacting with rock, just like the hydrothermal vents on Earth's ocean floor. What makes these vents so tantalizing isn't just their heat, it's the chemistry. On Earth, deep-sea hydrothermal systems like the Lost City vent field are teeming with life, sustained not by sunlight but by chemical energy. Microbes convert dissolved minerals like hydrogen and sulfur into fuel, forming the base of an entire ecosystem that thrives in total darkness. Enceladus's vents appear to be doing the same thing. Cassini's instruments found molecular hydrogen and organic compounds in the plumes, key ingredients for a process called chemosynthesis, where life harnesses chemical reactions rather than sunlight for energy. The parallels are impossible to ignore. If life can flourish around Earth's vents, why not on Enceladus? The moon's ocean is salty, alkaline, and rich in the building blocks of life. Conditions some scientists argue might be even more favorable than Earth's early oceans. And unlike Jupiter's moon Europa, whose ice shell is miles thick, Enceladus occasionally delivers samples of its ocean directly into space, offering us a free ticket to study its hidden depths without drilling. Yet the most startling detail might be the vent's longevity. On Earth, hydrothermal systems shut down as tectonic plates shift, but Enceladus's vents could have been operating for billions of years, sustained by the relentless flexing of Saturn's gravity. That's an unimaginable stretch of time for life to emerge and evolve, far longer than it took on Earth. The question now isn't just whether Enceladus could harbor life, but how we might find it. Future missions like NASA's proposed Enceladus Life Finder aim to analyze plume material with even greater precision, hunting for amino acids or lipids molecules that would scream biology. Others dream of sending a submersible through the ice, exploring this alien ocean firsthand. Until then, Enceladus remains a silent enigma, its vents whispering promises of discoveries that could redefine our place in the cosmos. Every plume is a message in a bottle tossed into the void, waiting for us to decode its secrets. And if life is there, clinging to those mineral-rich towers in the dark, it would prove one thing: the universe isn't just hospitable to life, it's insistent on it. Neptune's moon Triton shouldn't exist, at least not the way we see it today. A captured Kuiper Belt object turned ice-covered oddball. This world defies expectations at every turn with its backward orbit, its frozen nitrogen plains, and most strikingly, its explosive geysers that blast towering plumes of dark material 8 miles high into the thin atmosphere. These aren't eruptions of water or lava like those on Earth or Io, they're colossal jets of nitrogen gas, powered by something as simple and profound as sunlight. What makes these geysers so extraordinary is their fuel. Triton's surface is a vast reservoir of frozen nitrogen, methane, and carbon monoxide, so cold it behaves like bedrock. But when Neptune's distant summer arrives, the sun's feeble warmth penetrates just enough to vaporize patches of this exotic ice. The nitrogen doesn't just melt, it transforms directly from solid to gas in a process called sublimation, building pressure beneath the moon's translucent surface ice until it cracks open, releasing furious jets that carry dark, organic-rich dust upward like a cosmic shotgun blast. Voyager 2 spotted these plumes back in 1989, their dark streaks staining the bright ice like ink spilled across snow, but the mechanics behind them remain eerily alien. Here's where Triton's geysers get even weirder. They're not random. Unlike the chaotic volcanoes of Io or the intermittent plumes of Enceladus, Triton's eruptions follow seasonal patterns tied to its 40-year-long summer. As sunlight intensifies over decades, it warms subsurface layers of nitrogen ice, creating pressurized pockets that eventually burst through the frozen crust. The plumes don't shoot straight up. Either Triton's feeble gravity and thin atmosphere allow the gas to curve in parabolic arcs, trailing dark particles that drift for miles before settling back to the surface. It's a slow-motion fireworks display on a planetary scale, with each eruption unfolding over months. The real mystery lies in the dark material itself. Unlike the pristine ice around it, the geyser's debris is rich in complex organics, likely formed when solar radiation bombards Triton's surface chemistry over eons. Some scientists speculate these compounds might even hint at probiotic processes, though with surface temperatures hovering near absolute zero, life as we know it is almost impossible. Instead, the geysers offer something equally valuable: a glimpse into how volatile ices behave under extreme conditions, sculpting landscapes across the outer solar system. Triton's geysers are more than just a geological curiosity, they're a lesson in cosmic recycling. The nitrogen they expel doesn't escape into space, it falls back as frost, replenishing the moon's icy cap in a slow, rhythmic cycle. This delicate balance makes Triton one of the few places beyond Earth where we see weather systems driven not by water, but by an alien element's phase changes. And as Neptune's seasons continue their slow march, these geysers will keep erupting, a silent testament to the universe's ability to create dynamism even in the coldest, most distant corners. What's most humbling is realizing these plumes might not be unique. As we discover more icy worlds in the Kuiper Belt and beyond, Triton stands as a prototype, a frozen laboratory showing how nitrogen, methane, and sunlight can conspire to transform a dead moon into something unexpectedly alive. Every eruption is a reminder that even in the darkest reaches of the solar system, there's no such thing as true stillness, only pauses between bursts of cosmic energy. Some stars don't just drift through the galaxy, they escape it, rocketing into the void at speeds so extreme, not even the Milky Way's gravity can hold them back. These are hypervelocity stars, cosmic fugitives flung from their stellar neighborhoods at over 1 million miles per hour, fast enough to cross the distance between Earth and the Moon in less than 15 minutes. And the most surprising part, many of them owe their breakneck speeds to a gravitational slingshot from the supermassive black hole lurking at our galaxy's heart. The story begins near Sagittarius A, the 4 million solar mass black hole anchoring the Milky Way center. when a binary star system, two stars orbiting each other, wanders too close, the black hole's immense gravity can tear the pair apart. One star gets captured, swirling into an unstable orbit, while its companion is violently ejected, catapulted outward like a pebble from a slingshot. The energy transfer is so brutal, the ejected star can reach speeds exceeding 500 kilometers per second, 3 times faster than the Sun's motion through the galaxy. The first of these rogue stars, known as S5HVS1, was discovered in 2005, racing away at nearly 2 million miles per hour, with a trajectory proving it was flung from the galactic core. But not all hypervelocity stars come from black hole encounters. Some are survivors of supernova explosions, where the sudden loss of a companion star's mass sends the remaining one careening off like a released rubber band. Others might be intergalactic trespassers, hurled into the Milky Way after ancient collisions between dwarf galaxies. One star, dubbed J09374, was caught speeding toward us at over 1,000 kilometers per second, likely ejected from the Large Magellanic Cloud during a close encounter with another galaxy. The real challenge isn't just spotting these stellar speedsters, it's figuring out where they're headed. Some will eventually leave the Milky Way entirely, condemned to drift through the intergalactic void, cold and alone for eternity. Others might slow just enough to be recaptured by the galaxy's outer halo, joining a sparse population of stars in the cosmic boonies. A handful, like the white dwarf LP400093, are even on trajectories that could take them clear out of the local group into the emptiness between galaxy clusters. Yet hypervelocity stars aren't just celestial curiosities, they're cosmic breadcrumbs. By tracing their paths backward, astronomers can map the Milky Way's gravitational field in unprecedented detail, revealing hidden pockets of dark matter or even the scars of long-ago galactic mergers. Their compositions tell stories too. Some are young, blue, and massive, suggesting a violent birth near the galactic center, while others are ancient and metal-poor, hinting at origins in long-dead dwarf galaxies. Each one is a messenger, carrying clues about the forces that shaped our corner of the universe. What's most humbling is the sheer scale of their journeys. These stars aren't just moving fast, they're crossing distances so vast, their trajectories will outlast the Milky Way itself. Long after Earth is gone, long after the Sun dies, these stellar outcasts will still be streaking through the darkness, silent witnesses to a galaxy that couldn't hold them. And somewhere out there, right now, another star might be feeling the black hole's pull, poised to join their ranks, a cosmic refugee in the making. In a sea of massive, majestic galaxies, there exists a cosmic oddity so small and unassuming, you might mistake it for a flaw in the telescope's lens, a tiny, glowing speck no bigger than a fraction of our Milky Way. Yet these so-called green pea galaxies punch far above their weight, blazing with the fury of 1,000 newborn stars packed into a space barely larger than a star cluster. First discovered in 2009 by citizen scientists combing through data from the Sloan Digital Sky Survey, these emerald-hued anomalies get their name from their vivid color and diminutive size, appearing no larger than a pea in telescopic images. But don't let their quaint nickname fool you. What they lack in scale, they make up for in raw, unfiltered cosmic chaos. What makes green peas so extraordinary is their resemblance to the universe's toddler years. While most modern galaxies form stars at a leisurely pace, these compact powerhouses churn out stellar nurseries at rates comparable to the earliest galaxies, just a few billion years after the Big Bang. Their green tint comes from ionized oxygen, a telltale sign of ferocious star formation where ultraviolet radiation from massive young stars tears electrons off atoms, causing them to glow like neon signs in the cosmic void. But here's the twist: green peas aren't ancient relics. They're surprisingly nearby, some just 1 to 5 billion light-years away, making them living fossils that let us study the conditions of the early universe without peering to its edge. The secret to their hyperactivity lies in their simplicity. Unlike mature galaxies cluttered with complex structures, spiral arms, bulging cores, and dark matter halos, green peas are stripped-down primordial engines. Their small size means supernova explosions can easily blow gas outward, triggering chain reactions of star formation as the material collapses back in. Imagine a pot of water boiling violently on a stove. The more heat you apply, the more the bubbles erupt. In green peas, stellar winds and explosions keep the galactic pot simmering at a fever pitch, preventing the calm needed to settle into a more orderly spiral or elliptical shape. Yet the most tantalizing detail isn't just how they form stars, it's what they're doing to their surroundings. Green peas leak staggeringly large amounts of ultraviolet radiation, punching holes in their own gas reservoirs and ejecting material into intergalactic space. This violent outflux mimics the processes that ionized the universe's early hydrogen fog, a pivotal era called reionization that transformed the cosmos from opaque to transparent. In essence, these tiny galaxies are local laboratories for one of the universe's most transformative epochs, offering clues about how light first broke free to travel across space. The irony, green peas might be more common than we thought. Recent surveys suggest similar ultra-compact, star-bursting galaxies could be hiding in plain sight, overlooked because of their small size or dismissed as artifacts. Some even speculate they represent a fleeting phase in galactic evolution, a turbulent adolescence that most galaxies outgrew billions of years ago. Whether they're cosmic stragglers or late-blooming oddities, one thing's certain: these tiny emerald fireballs remind us that sometimes the universe's most profound secrets come in the smallest, most unassuming packages. And as telescopes grow sharper, who knows what other peas might be scattered across the cosmic vine, waiting to be plucked. Among the most volatile and radiant stars in the cosmos, luminous blue variables stand out like cosmic powder kegs, hypergiants teetering on the edge of self-destruction, capable of erupting with the force of a stellar supernova without ever quite crossing that threshold. Take Eta Carinae, the poster child of this chaotic class. In the mid-19th century, this star unleashed the Great Outburst, briefly becoming the second brightest object in the night sky despite being 7,000 light-years away. For over a decade, it vomited enough material to forge multiple solar systems, ejecting 20 times the mass of our Sun in a cataclysm that left behind the Homunculus Nebula, a glowing hourglass of gas and dust still expanding outward at nearly 2 million miles per hour. What makes these stars so unstable is a brutal tug-of-war between radiation and gravity. Luminous blue variables pack up to 150 solar masses into a single star, so massive their cores churn out enough energy to make our Sun look like a flickering candle. That radiation pushes outward with such force, it threatens to rip the star apart from within. Yet gravity, relentless and unyielding, counters this by compressing the star's core to unimaginable densities. The result, a perpetual state of rebellion where the star's outer layers swell and contract unpredictably, like a cosmic heartbeat gone haywire. During particularly violent episodes, these stars can shed entire suns' worth of material in sporadic eruptions, shrouding themselves in thick, opaque shells that temporarily mask their brilliance before the next explosion blows them clean. The mechanics behind these outbursts defy textbook stellar physics. Unlike supernova, which mark the death throes of a star, luminous blue variables experience partial detonation surface explosions powerful enough to reshape nebulae but insufficient to obliterate the star entirely. Some theories suggest these eruptions occur when radiation pressure overwhelms the star's surface, causing its outer layers to peel away like an overripe fruit. Others point to instabilities in the star's core, where nuclear reactions flicker between extreme states, triggering seismic waves that ripple outward and destabilize the entire structure. Eta Carinae isn't alone in its tantrums. Stars like P Cygni and S Doradus follow similar scripts, flickering between extreme brightness and abrupt dimming as they cough up shells of ionized gas. What's haunting is how little warning these eruptions provide. One day, the star might appear calm. The next, it's vomiting enough ultraviolet radiation to sterilize nearby star systems. But the most unsettling question isn't just how these stars behave, it's what they'll become. Luminous blue variables are thought to be the precursors of some of the universe's most cataclysmic events. Pair instability supernova, where the core becomes so hot it spontaneously creates matter-antimatter pairs, leading to a runaway explosion that leaves nothing behind. Others might collapse directly into black holes, skipping the supernova stage entirely. For now, these stars serve as cosmic laboratories, offering glimpses into the extreme physics that govern the universe's most massive objects. Every eruption, every ripple of ejected gas is a lesson in stellar mortality, a reminder that even the brightest giants live on borrowed time, dancing on the knife's edge between radiance and ruin. And when the next great outburst comes, it might just rewrite our understanding of stellar evolution in real time. Imagine a star so dense, a single teaspoon of its material would weigh 1 billion tons, and then crank its magnetic field up to 1,000 trillion times stronger than Earth. That's a magnetar, the universe's ultimate cosmic power plant, capable of unleashing flares so bright they outshine our entire galaxy for a fraction of a second. These aren't just stellar tantrums, they're magnetic apocalypses where the very fabric of space-time twists under forces so extreme, physics textbooks crumple under the weight of their description. At the heart of every magnetar lies a neutron star, the collapsed core of a once massive star that went supernova. What sets magnetars apart is their unimaginable spin. Born rotating at dizzying speeds, some completing full revolutions in milliseconds, these stellar corpses amplify their magnetic fields through a dynamo effect, like a cosmic generator gone haywire. But here's where things get violent. When that magnetic energy builds past its breaking point, the star's rigid crust, already under unimaginable strain, snaps like a brittle pane of glass. The resulting starquake releases pent-up energy in a millisecond blast of X-rays and gamma rays visible across the universe. The numbers defy belief. In 2004, a magnetar flare from 50,000 light-years away briefly ionized Earth's upper atmosphere, despite being halfway across the galaxy. Another in 1979 flooded detectors with so much radiation, astronomers initially mistook it for a nuclear detonation in space. For that split second, it outshone the full moon in gamma rays, delivering more energy than our sun will emit in 250,000 years. But what fuels these explosions isn't just raw power, it's quantum rebellion. Magnetic fields are so intense, they distort the behavior of particles at the subatomic level. Electrons, normally content to orbit atomic nuclei, get forced into bizarre, elongated paths, emitting radiation just to exist. Protons and neutrons inside the star's core align like microscopic compass needles, storing energy until the entire system reaches critical tension. When the crust fractures, it's like uncorking a bottle of shaken champagne, except the bubbles are relativistic particles, and the bottle is the star itself. The aftermath is just as surreal. Some magnetar flares leave behind glowing afterglows where magnetic fields reconnect, sparking secondary bursts for weeks. Others emit eerie, rhythmic pulses not from rotation, but from seismic waves rippling across their surfaces like gongs struck by invisible hammers. And in rare cases, the explosions rewrite the star's own magnetic architecture, turning a once deadly magnetar into a quieter neutron star, as if the universe itself hit a reset button. For all their fury, magnetars are fleeting cosmic firecrackers. Of the 30 billion neutron stars estimated to exist in our galaxy, only a few dozen are confirmed magnetars, likely because their extreme fields decay within 10,000 years, a blink in cosmic time. Yet while they burn bright and fast, their flares serve as celestial laboratories, letting us test theories about matter, magnetism, and gravity under conditions no Earth experiment could ever replicate. Every time one erupts, it's a reminder that even in death, stars find ways to set the universe ablaze. Deep in the cosmos, some stars don't just shine. They pulse like living hearts, their light rising and falling in precise, rhythmic beats. These aren't erratic flickers or random flares. They're the steady cadence of so-called heartbeat stars, binary systems where two stars orbit so close. Their gravitational embrace distorts their shapes like cosmic taffy, creating a luminous dance visible across the universe. The phenomenon was first spotted in 2008 by NASA's Kepler Space Telescope, which detected strange, repeating patterns in stellar brightness, curves so smooth and regular, they resembled an electrocardiogram tracing the pulse of a celestial giant. Unlike typical variable stars, which dim and brighten due to internal processes, heartbeat stars owe their flicker to tidal forces. As the stars swing around their shared center of mass, their mutual gravity stretches them into egg-like shapes at closest approach, then lets them relax into spheres as they pull apart. This back-and-forth distortion changes how much surface area faces Earth, making the system appear to throb in sync with its orbit. What makes these systems truly mesmerizing is their precision. Take Koi 54, one of the first heartbeat stars discovered. Every 41 days, its two ultra-hot stars, each over twice as massive as the Sun, pass within a few million miles of each other, close enough that their gravitational pull raises tidal bulges thousands of miles high. The resulting brightness spike isn't subtle. Koi 54 light swells by nearly 10% at peak, a surge so predictable you could set your watch by it. But the real magic happens beneath the surface. The same forces that warp the star's shapes also send seismic waves rippling through their interiors, like a bell struck by an invisible hammer. These vibrations reveal themselves as tiny, rapid flickers superimposed on the main pulse subharmonics that let astronomers listen to the star's internal structure, a technique called asteroseismology. The universe loves variety, and heartbeat stars are no exception. Some, like Macho 80, 7443, 1718, take the drama to extremes. Here, the stars orbit so tightly that their mutual gravity doesn't just distort them, it rips material from their surfaces, creating glowing bridges of plasma that stretch between the pair like cosmic tetherballs. Others, like HD 174884, showcase resonant orbits where the star's rhythmic tug of war creates harmonic overtones in their light curves, turning their brightness variations into complex cosmic symphonies. Yet the most tantalizing aspect of these systems isn't just their beauty, it's what they teach us about stellar evolution. Heartbeat stars are cosmic laboratories, laying bare how gravity, rotation, and magnetism interact in extreme environments. Their tidal forces can churn internal fluids, mixing elements that would otherwise remain sequestered in their cores. Some even exhibit Doppler beaming, where the motion of their surfaces blue shifts or red shifts their light slightly, adding another layer to their pulsating signals. For astronomers, every heartbeat star is a gift, a natural oscilloscope probing physics we could never replicate on Earth. And as telescopes grow more sensitive, we're finding them in ever stranger configurations. Trios, quadruples, even systems where the heartbeat is drowned out by the roar of a black hole companion. Each discovery peels back another layer of the mystery, reminding us that even in the vast stillness of space, rhythm is everywhere, if you know how to listen. Black holes devour everything that crosses their event horizon. But what if somewhere in the universe the reverse is happening? Enter the white hole, a hypothetical cosmic gusher where matter and energy erupt outward instead of vanishing forever. If black holes are the universe's drains, white holes would be its fire hoses, spewing material into space with no way to enter them. The math allows for this bizarre possibility. Einstein's equations describe white holes as perfectly valid solutions to general relativity, essentially black holes running backward in time. But do they exist, and what would they look like if they did? Picture a singularity that refuses to stay hidden. Unlike its dark counterpart, a white hole's event horizon would act like an impenetrable force field, repelling all matter and radiation. Anything attempting to cross inward would be violently rejected, while inside, trapped material would be expelled at unimaginable speeds. Some theories suggest these outbursts could mimic the Big Bang itself, localized explosions of space-time birthing new universes. Others propose that white holes might explain mysterious cosmic phenomena like gamma-ray bursts, those fleeting but ultra-energetic flashes that light up the distant universe without warning. The trouble is, white holes defy thermodynamics. While black holes form naturally from collapsing stars, white holes would require some mechanism to reverse entropy, essentially unscrambling an egg on a cosmic scale. One wild explanation ties them to quantum gravity. When a black hole evaporates via Hawking radiation, a process that takes longer than the current age of the universe for typical ones, some models suggest it could rebound as a white hole in its final moments, a last gasp of spacetime refusing to let information die. These remnant white holes would be microscopic but staggeringly dense, potentially leaving behind fingerprints in high-energy particle collisions or fast radio bursts. Then there's the multiverse angle. If our universe's Big Bang was the white hole in point of a black hole in another cosmos, it could explain why our physical constants seem so finely tuned. We're literally inheriting the conditions of a parent universe's collapse. It's a dizzying thought. Every black hole here might incubate a new reality elsewhere, making white holes the birthmarks of cosmic reproduction. Yet for all their theoretical appeal, no observed object fits a white hole's profile. Some researchers argue they're mathematical curiosities with no physical reality, while others hunt for them in anomalies like the delayed gamma-ray echoes from deep space or unexplained voids where galaxies seem to flow away from a central point. Until we detect one, or rewrite the rules of physics, white holes remain the universe's most tantalizing what-if, a reminder that even gravity's grip might have an escape clause. Beneath the smooth, predictable fabric of spacetime we experience every day lies a seething, turbulent underworld, a frothing ocean of energy where reality itself flickers in and out of existence. This is quantum foam, the universe's most chaotic dance floor, where the rules of classical physics dissolve into pure, unfiltered uncertainty. At scales 100 billion times smaller than an atom, spacetime isn't the calm grid we imagine. It's a storm of virtual particles erupting in spontaneous bursts, colliding, annihilating, and rewriting the very concept of empty space. Picture the void as anything but empty. Thanks to Heisenberg's uncertainty principle, nature's ultimate loophole, particle-antiparticle pairs can borrow energy from nothingness, blinking into existence just long enough to satisfy quantum math before vanishing again. These aren't mere mathematical quirks, their effects ripple upward into our macroscopic world. Ever wonder why atoms don't spontaneously collapse? It's because this ceaseless froth, this quantum foam, creates a seething pressure that stabilizes the orbits of electrons like an invisible cosmic foam cushioning reality itself. The wildest implication, spacetime itself might be pixelated at this scale. Just as a computer screen disguises individual pixels as a smooth image, what we perceive as continuous space could be built from discrete, frothy bubbles at the Planck length, a mind-boggling 10 to the minus 35 meters. Gravitational waves passing through this foam would theoretically get jostled, like light twinkling through turbulent air, a potential clue we could detect with future experiments. Some models even suggest black holes aren't infinitely dense points, but knots of ultra-twisted quantum foam where spacetime tangles into fundamental threads. Yet probing this chaos directly remains one of physics' greatest challenges. The energy required to see the Planck scale is a quadrillion times beyond what our mightiest particle colliders can muster. For now, we glimpse its shadows through Casimir effect experiments where unseeable virtual particles push metal plates together, or in the faint glow of Hawking radiation at black hole edges, where quantum foam's turbulence gets stretched into detectable particles. What makes quantum foam so revolutionary isn't just its strangeness, it's the doorway it opens. If space-time has structure at this level, it hints at a deeper theory weaving together quantum mechanics and gravity, perhaps through loops, strings, or something we haven't yet imagined. Every virtual particle pair is a fleeting whisper from the universe's most fundamental layer, reminding us that nothing, not even the vacuum of space, is ever truly at rest. And somewhere in that ceaseless froth, the answers to reality's biggest mysteries might be bubbling, unseen but undeniable, beneath the surface of everything. What if everything you see, touch, and experience, every star, planet, and even your own thoughts, is nothing more than an illusion, a shimmering projection cast from the edge of reality? This is the radical promise of the holographic universe theory, a concept so mind-bending, it redefines the very fabric of existence. At its core, the theory suggests our three-dimensional world might be a cosmic hologram, an elaborate illusion encoded on a distant, two-dimensional surface like a movie projected from the universe's ultimate screen. The idea first gained traction in the 1990s when physicists studying black holes stumbled upon a bizarre mathematical consistency. As they calculated the information content of a black hole's event horizon, the point of no return, they realized something extraordinary. All the data describing objects swallowed by the black hole could be perfectly encoded on its two-dimensional surface like a cosmic fingerprint. No information was lost, it was simply translated into another form. This discovery, known as the holographic principle, soon spiraled into a far grander speculation. What if the entire universe operates the same way? Think of it like a credit card hologram, those shimmering images that appear three-dimensional when tilted, even though they're printed on a flat surface. In the holographic universe, every particle, every force, even the passage of time could be analogous to that illusion, emerging from interactions on a distant, flat boundary we can't perceive. The universe wouldn't just contain holographic properties, it would be one with all the richness of our 3D reality unfolding from a 2D code. But how could this possibly work? The mathematics points to entanglement, the quantum phenomenon where particles remain mysteriously linked across vast distances. Every interaction in our 3D world might trace back to entangled bits of information on that 2D boundary, like shadows cast by puppets on a cave wall. This would mean the solidity of your body, the vastness of galaxies, even the flow of time itself, are all emergent phenomena, secondary to the deeper, flatter layer of reality where the true computations of existence occur. The implications are staggering. If the holographic principle holds, it could solve one of physics' greatest paradoxes, the clash between quantum mechanics and gravity. In this framework, gravity wouldn't be a fundamental force but a side effect of the hologram's pixelation, like the graininess of an image when magnified too far. String theorists have even proposed that the extra dimensions their models require might not be out there at all. They could be mathematical artifacts of this 2D to 3D translation, hidden in the fine print of reality's code. Yet the theory isn't without its skeptics. Some argue it's a beautiful metaphor without experimental proof, while others point to the cosmic microwave background for clues. If spacetime has a pixelated holographic structure, there should be tiny, fundamental limits to how precisely we can measure it, like a cosmic resolution limit. Searches for this pixelation noise are ongoing, with some studies claiming tentative hints in the afterglow of the Big Bang, though nothing definitive. Perhaps the most haunting question the holographic universe raises isn't about physics but perception. If we're living in a projected reality, what or who is the projector? Is the cosmos the creation of some higher dimensional entity, or is it a self-sustaining computation, a universe that encodes itself? Every time you feel the weight of a book in your hands or watch a sunset, you might be interacting with the most sophisticated illusion of all, a shadow play written in the language of quantum bits, flickering into existence one infinitesimal pixel at a time. Imagine waking up one day not in your bed, not even in a human body, but as a lone, disembodied brain floating in the void of space. No past, no future, just a flicker of consciousness convinced it's lived a full life with memories, emotions, even this very thought. Only to dissolve back into chaos moments later. This isn't the plot of a sci-fi nightmare. It's the Boltzmann brain paradox, one of cosmology's most unsettling thought experiments, forcing us to question whether reality itself might be a fluke. The paradox traces back to Ludwig Boltzmann, the 19th century physicist who connected entropy to the arrow of time. He proposed that in an infinitely old universe, random thermal fluctuations could occasionally arrange particles into orderly structures, like assembling a perfect sandcastle by shaking a beach. Statistically absurd, absolutely, but given enough time, even the impossible becomes inevitable. Fast forward to modern cosmology, and this idea takes a surreal twist. If entropy allows for random order, could it conjure a fully self-aware mind from the quantum noise, complete with false memories of a universe that never existed? Here's where physics collides with philosophy. A Boltzmann brain wouldn't form through evolution or biology. It would be a freak accident, a momentary alignment of particles mimicking the exact neural configuration needed for consciousness. And in an infinite, eternal universe, these brains would statistically outnumber real, biologically evolved minds by an unimaginable margin. So why aren't we Boltzmann brains? The question upends everything. If the cosmos is truly infinite, odds are you are far more likely to be a fleeting fluctuation than a product of 14 billion years of cosmic evolution. Critics argue this is a reductio ad absurdum, a sign our theories are missing something fundamental. Maybe the universe isn't infinite, or perhaps quantum gravity imposes limits on fluctuations we haven't discovered. Others propose the paradox hints at deeper truths, that consciousness itself might be a cosmological constant, woven into the fabric of reality in ways we don't yet grasp. Some interpretations of quantum mechanics even flirt with the idea that observation creates reality, making the Boltzmann brain not just a glitch, but a dark mirror of our own existential uncertainty. The most haunting implication, there's no way to disprove it, a Boltzmann brain's hallucinated reality would be indistinguishable from genuine experience. Every memory, every scientific discovery, even this sentence could be the dying ember of a mind that never had a body, a universe, or a past. It's the ultimate skeptic's trap, a puzzle where the only escape might be accepting that some questions exist to remind us how much we don't know. Yet the paradox isn't just nihilistic navel-gazing. It's a stress test for our models of the cosmos. If the mere possibility of Boltzmann brains breaks our physics, perhaps it's time to rethink assumptions about infinity, entropy, or even the nature of time itself. After all, reality feels too consistent, too coherent to be a dice roll. Or maybe that's exactly what a Boltzmann brain would think. Every story has an ending, even the universe's. But how this cosmic tale concludes isn't just a footnote in astrophysics. It's a grand drama playing out in slow motion, dictated by invisible forces we're only beginning to understand. The universe's fate hinges on a tug of war between expansion and gravity, between dark energy's relentless push and matter's stubborn pull, and right now the outcome is anything but certain. Take the Big Crunch, a scenario as dramatic as it sounds. Picture the universe's expansion not just slowing, but reversing, galaxies rushing back toward each other like a film played in reverse. As space contracts, temperatures soar, stars melt into plasma, atoms shatter into subatomic particles, and eventually all matter collapses into a singularity, a mirror image of the Big Bang. It's poetic symmetry, a universe born from fire returning to fire. This idea once dominated cosmology back when astronomers assumed gravity would eventually overcome expansion. But then came the bombshell discovery in the late 90s. The universe isn't just expanding, it's accelerating. Dark energy had entered the chat, and with it, the Big Crunch's odds dwindled to near zero. Yet some theories still leave room for a comeback. If dark energy's strength isn't constant, if it weakens over trillions of years, gravity might yet have the final say. Then there's heat death, the universe's slow fade to black. In this scenario, expansion never stops. Galaxies drift apart until their light can no longer reach each other. Stars exhaust their fuel, black holes evaporate via Hawking radiation, and space cools to absolute zero, a uniform graveyard of scattered particles too weak to interact. Time itself becomes meaningless as every possible energy exchange has already occurred. It's not an explosion or implosion, but an endless sigh. This bleak outcome currently tops the probability charts, supported by measurements of dark energy's consistency. But even here, mysteries linger. Quantum fluctuations could give an unfathomable timescale spontaneously birth new universes, like bubbles forming in an infinite void. The cosmos might die, only to unknowingly plant the seeds for its own rebirth. Most terrifying of all is the Big Rip, dark energy's ultimate victory. Imagine it growing stronger over time, eventually overpowering not just galaxies but stars, planets, and even atomic bonds. In the final moments, space-time itself shreds at the seams. 1 millisecond, you're here. The next, every quark in your body is flung irretrievably apart as the fabric of reality disintegrates. While observational evidence currently makes this the least likely scenario, it forces us to confront dark energy's true nature. Is it really a constant, as Einstein's cosmological constant suggests? Or could it evolve into something far more destructive? The answer lies in the elusive equation of state for dark energy, a value that determines whether it's a steady force or a growing menace. But beyond these textbook scenarios, wilder possibilities emerge. Some models suggest vacuum decay, where a quantum fluctuation creates a true vacuum bubble that expands at light speed, rewriting the laws of physics as it goes. Others propose cyclic universes, endlessly bouncing between expansion and contraction, or a multiverse where our cosmos is just one temporary flap in an infinite cosmic quilt. The most radical idea, that time's arrow might not be fundamental at all, just an emergent property of our particular cosmic epoch, destined to reverse or vanish entirely. What makes these questions more than philosophical exercises is how they're already shaping our present understanding. The universe's fate isn't some distant abstraction. It's encoded in the redshift of galaxies, the afterglow of the Big Bang, and the bending of light around galaxy clusters. Every observation narrows the possibilities, but the finish line remains out of sight. One thing's certain, the cosmos doesn't owe us a happy ending. Its finale might be fiery, frozen, or fractured, or something beyond our current imagination. And that uncertainty is precisely what makes the search so thrilling. After all, in confronting the universe's mortality, we're really grappling with our own ephemeral place within it. From runaway black holes painting the cosmos with stolen starlight to vanishing galaxies and diamond planets, the universe has proven itself a master of the bizarre. We've journeyed through 50 of its strangest enigmas, each one defying expectations, bending physics, or whispering secrets we're only beginning to decode. Yet here's the humbling truth: these mysteries are just the flickering tip of a cosmic iceberg. For every phenomenon we've named, there are countless others lurking in the shadows, waiting to shatter our understanding all over again. Take something as fundamental as dark matter. After decades of hunting, we still don't know what it is, only that it sculpts galaxies like invisible hands. Or consider those eerie fast radio bursts pulsing across billions of light-years with no discernible pattern. Are they the screams of colliding neutron stars or something far more exotic? Even in our own solar system, surprises abound. Saturn's hexagon, Mars's methane whispers, Europa's plumes all remind us that familiarity breeds complacency. The planets we think we know still guard jaw-dropping secrets. This isn't just a list of oddities, it's an invitation. An invitation to stay awestruck, to question relentlessly, and to embrace the unknown as the universe's most thrilling frontier. Because every time we think we've got it figured out, the cosmos throws a curveball. Maybe it's a star that flickers like a broken street lamp, or a void so vast it shouldn't exist. Maybe it's the chilling possibility that we're living in a hologram, or that reality itself could be a fleeting quantum fluctuation. So here's to the unanswered questions, the cosmic riddles that keep scientists up at night and fuel our collective imagination. If this journey through the universe's weirdest wonders has sparked your curiosity, you're not alone. Hit subscribe to dive deeper into the unknown with us, and drop a comment below. Which mystery left you utterly spellbound? Was it the Phantom Islands on Titan, the zombie stars cheating death, or something even stranger? The universe isn't done surprising us, and neither are we. Until next time, keep looking up. The next great cosmic revelation might be just over the horizon.